All right, let's get started. I hope everyone can hear me and the people in the Zoom call as well. Welcome to this workshop that we've called BigMAC, Big Model Adaptation for Computer Vision. As you can see, these are the speakers we'll be having today. Organizers are myself, Tenda, who's also around. I think he's just checking in the queue, Mathilde, Philip, and Serge Belangi. The schedule for today. We won't be having any BigMACs, but this is the alternative program, which is hopefully equally as good. You can see the same program also on the website. You have also abstracts about the talks that you will be hearing. And I'm now at the part of the welcome and introduction, so welcome. And now to introduce you to why we're even having this workshop. So everyone knows this plot. No one knows exactly where that point is exactly for GPT-4. It's somewhere probably 1 trillion, 1.6 trillion, something like that. What we know is that they've grown a lot. And
hello everyone. Whoa. Welcome to ICCV'23. Disciplinary results workshop.
Okay. Okay, yeah, I think you're all right, in the right room. Thanks. All right. And yeah, there's people also analyzing these trends, and you can actually see quite statistically significantly nicely that there's 3 different eras. There's the pre-deep learning era of where model parameters are growing.
To clarify, P1 is disciplinary false workshop room, and P2 is disciplinary nodes workshop room.
Okay. They didn't mention our room, which is a bit sad, but okay. Pre-deep learning era, deep learning era, and large-scale era. They all follow different trends, but they're all going upwards, right? Now, we've heard this enough from Twitter that we might have been thinking that this is just NLP, but this is not the case, right? We've seen all kinds of deep learning systems grow in size. So we all know the games deep learning systems from AlphaZero, AlphaGo, etc. But increasingly, we're seeing this in Vision too. So here's a plot of the OG Vision transformer, how that has increased in size. So for example, with the newest paper with 22 billion, they've arrived at 22 billion just for a vision encoder, right? And they've written that it required 1,000 TPU V4 chips, which is a lot. But not only that, since sort of transformers arrived in vision, we've been scaling all kinds of vision models. So it can be conf architectures, but also units, right, with stable diffusion, etc. It just seems to be a very good recipe at this point. And another good recipe seems to be the combining of vision systems with LLMs. So here's a plot from that we just had right now. And now we have this dramatic increase in parameters when we add a LLM to this thing, right? So this is in scale where you would end up with Flamingo, which has combined a 70 billion LLM with a vision system. And this is Flamingo. And now there's folks at Google that make it 560 billion, right? And so the vision systems keep on increasing in size and they keep on getting better. So it seems there might be no clear way back, and who knows how big GPT-4 even is. Most of the work has these sort of architectures by combining vision into LLM models in some smart way, and then things just seem to be better. Here's some references. They're by no means complete, but I thought they might give you a starting point if you're interested in this. So what I believe I've shown you can be basically summarized as follows. You have your recipe of transformers. Then what you add is a bit of parameters, a bit more of data, and a tiny amount of GPUs. And then for good measure, you add some more parameters and maybe some more parameters. And it's a well-known recipe, and it just works, right? It works so well that in NLP, they actually know exactly or know pretty well, if you add this much more compute, this is the performance you will get. We're not quite there in vision yet, I believe. But this workshop talks more about, or will be talking more about all kinds of ways of adapting. And this will become, especially for the academic community, but also for industry, more and more important. Where the goal is that we require very little work, less parameters, perhaps less GPUs, but still have a large effect. And now I will end my talk just to give a few notes of existing ways of fine-tuning. And I'm sure that today we'll learn a lot more about these and about completely new ways of using models. So just for everyone, this is the old school way of using models, right? You fully fine-tune a model. Limited fine-tuning has been around for a long time as well, not just as an evaluation of representations, but also as a way to use models. So you keep a majority of the model just frozen and then fine-tune from layer number X or of the last layer. Of course, people have been using no fine-tuning as well, just to use embeddings and get the nearest neighbors as recommendations or as retrievals. But now there's this whole idea of parameter-efficient fine-tuning methods. So basically, if this huge block is your model, you want something that gives you a lot of leverage. And so here, ever since the first works on adapters, there have been a lot of works that show you just need a tiny amount of parameters to actually steer the behavior of these models. This could be in tiny one-by-one convolutions inserted into the models or residual MLPs, only fine-tuning batch norm or bias parameters, learning masks, and very popularly recently, especially in NLP, is the low-rank adaptation of matrix multipliers, especially with transformers. You have the key query value matrices, and you can just adapt these with very few parameters if you use low-rank updates. And this other prevailing, I would say, paradigm has been prompt or prefix learning, which, I mean, when at the beginning we had very manual, where we actually came up with words like trending on ArtStation to get very nice pictures in Stable Diffusion. But nowadays, these are typically learnable, directly optimized in continuous space, and can also be inserted at various places in the model. There's a bunch more, and I'm sure we'll be hearing very different paradigms as well today. Just this as an overview of what has been around. All right, and with that, I'll leave you with a schedule, and then I would like to welcome our first speaker for today, Neil Houlsby. Let me tell you something about this fella. So he's a senior staff research scientist at Google Google DeepMind Brain, I guess, in Zurich. And he has pioneered a lot of the works. So I'm sure we'll be hearing a lot of interesting things. And his talk title is, I don't have it here, Advances in Visual LLMs, something like that. Yeah, all right, great, thanks, welcome, please, thank you. So can you share your screen now? Actually, let me. Yeah, now it should work. I think you need to press here, weirdly enough. Yeah, works. Would you? Yeah, just unmute yourself there.
Hi, Neil. I think you are on mute. Neil, can you hear us?
Sorry, we can't hear you. We can't hear your voice.
Can you hear us now?
Yes, now
yes.
Okay.
Yes, now we can.
I'll just leave my laptop here. Does it work?
So this recipe works well. But the vision models can also be scaled, and it's also useful to do so. So this experiment comes from the Pali paper, and it shows models of 3 different sizes. The blue smallest model is normalized to a score of 0, and it consists of a 2 billion parameter vision model and a 1 billion parameter language model. As was observed in Flamingo, if one scales up the language model, that's the red bars, to a 13 billion parameter language model, we'll get to a large improvement of performance. And these are quite well-established benchmark tasks that plus 3% is quite significant. However, with only a 13% increase in overall model capacity, but where all that extra capacity was put on the vision model, one gets the same or greater increase in performance again. So this is an indication that it can be useful to look at how to scale vision models as well. So that's what I'm going to talk about in this slide. I'm going to talk about the Vision 22 billion parameter model that was mentioned in the introduction. And the goal of this work was just to see what would happen if one did attempt to scale a vision transformer up to LLM size models. And then I'm going to present 2 techniques for scaling much more efficiently. So the first work, scaling vision transformer to 22 billion parameters. Like I said before, the idea of this work was to train such a large model and see what happened, what would emerge if we did that. The model was trained on 4 billion unique images for a few epochs, so 10 billion images seen, and then we analyzed the representations or fine-tune it to various tasks and look at the properties of the model. The paper also describes quite a few tricks to make the training more efficient, but I won't go into those in this talk. That's kind of a talk in its own right. So the first property of large vision transformers is not an ideal one. It's instability. So what we found when we trying to scale the standard vision transformer recipe was that everything was fine and good up to about 8 billion parameters. But then at the 8 billion parameter size, after some time, not only did the validation loss start going up, but the training loss went up as well. And some weird stuff was happening with the gradient norms. So these looked rather difficult to train. This was an annoying problem to debug because you had to train for quite some time before one saw this problem. But one thing we noticed that correlated with this instability of training was the attention lodges reaching very large values, which resulted in one-hot, very low entropy attention distributions. When we saw this, we always saw this inability for the model to continue training. So the solution, although it took some finding, was actually fairly simple, is to add layer normalization after the query and key computations. Doing that results in the green curve, and everything trains nicely again. So this is a very simple thing to add if one's trying to train a larger model. It also helps smaller models because it allows a larger learning rate, and it's available in flags if anyone uses JAX or flags. So having done this, the first thing, of course, to do is to look at accuracy on some standard benchmark tasks. So this is 0-shot accuracy on ImageNet, clean images on the x-axis, and ObjectNet, which is pictures or images taken in the wild, on the y-axis. And as one might hope, the performance on both of these metrics continues to improve as the model scale increases. We also tried fine-tuning to ImageNet, which is a very popular thing to do. But here things look a little bit more worrying. We seem to have got stuck at around the 90% mark. But this is not too bad because at least the performance on the outer distribution data is going up. And it's also been studied that not only in the ImageNet dataset, there is about 10% label set noise. So one might not see improvements on some standard benchmarks and think that the scale is not working. In fact, when one looks at more challenging benchmarks, then one can see the difference. So what's causing this outer distribution improvement to performance? Well, at least one thing that we saw that was interesting that correlates with it is this shape texture bias. So this is a really interesting evaluation introduced a few years ago by Garahos et al. And so this evaluation involves classifying images like the following and saying whether the image is a cat or an elephant. And so if you try this yourself and you think the image is an elephant, then you're in the vast minority. Most people classify the image according to its shape and not according to its texture. However, Most vision models, recognition models in the last 10 years classify according to the texture of the image. So most CNNs would say that that image is an elephant. Now, on recent years, transformers and scaled up CNNs are starting to move towards a shape bias, so slightly away from texture bias and towards shape bias, maybe a more like 50-50, but still don't have anywhere near as strong shape bias as people do. So humans are all the way over on the right-hand side of the figure, and almost always classify according to the shape and not the texture. However, when we get to 22 billion parameters, what we observe is that all of a sudden the vision transformer starts to vastly prefer the shape of the object rather than the texture. So this is an interesting property that seems to then correlate with this outer distribution robustness. One other thing that was perhaps especially surprising is it is often observed that calibrations, this is the ability to correctly predict when it doesn't know, so assign accurate probabilities to a prediction, and for the actual number of times it's correct to match that probability, to be inversely correlated with accuracy. And indeed, within a single model class, that's sometimes the case. So if one looks at uncalibrated, unscaled calibration error, then one sees this trade-off. For example, these yellow squares, the more accurate ones, are more poorly calibrated. However, across model classes, if we look at the VID22B model, which is light blue, we can see that it is both better calibrated and more accurate, especially after temperature scaling. So this is somewhat reassuring. We plug the model in vivo into the Parley system, then again we see another improvement in performance. The Parley X model is not just a larger vision model, it's also a larger language model which has this performance, but the two go nicely together. So this was our main motivation to build these VLMs, and because we've seen that having scaled to 22B parameters, that one can get these nice properties. The question is how to do this more efficiently and more effectively. So we've been working on some techniques to try and train vision models in a faster manner. And the two I'm going to talk about today are this native fit, so native resolution training, and the soft mixture of experts model. So first, native fit. The use of transformers in vision has brought vision and language pipelines quite closer together, which has made training vision language models easier and more scalability on the vision side. However, there's still some substantial difference in the pre-processing that is performed. Typically, in computer vision, the pre-processing works as follows. You take your images that come in whatever size they come in, and then resize them all to a square, usually 224 by 224, but sometimes a different size. And of course, this has been very popular for a long time because it allows one to pack one's images into a batch and process that entire batch very efficiently with a convolutional neural network. But this style of pre-processing has a number of limitations. Firstly, you lose the aspect ratio, or you need to crop or pad your image and so that it becomes a square without distorting it. Secondly, you process the same number of pixels for every image. So it doesn't matter if the image is a big canvas with lots of details in it, or it's just a very simple image, single object, you always process the same number of pixels, which seems suboptimal. Third, if you want to do per image pre-processing, you need to end up with an image that is the same size as all the other images. So for example, a popular kind of pre-processing is to drop patches in a transform model, but you have to drop the same number of patches per image, or else you end up with images of different sequence lengths. And finally, for the vision transformer, once you've fixed your resolution and patch size, then your sequence length is fully specified, but you might want to train on a different sequence length, say a longer or shorter sequence length, because that might be more efficient on the hardware that you're using. And so none of these things are possible with a traditional pipeline. So the idea behind NAVIT is to use patch and pack, and this is just the simple application of ideas from example packing in language to computer vision. So it works as follows. When one's images come in, in whatever size they come as. And next, one performs the patching operation, so chopping the image up into 16 by 16 or 14 by 14 patches, as has become popular for vision transformers. Next, one can do whatever pre-processing one likes on top of the patches, and one of the most popular these days is token dropping. This allows one to save one's compute by not processing redundant tokens, and also it acts as some kind of regularization. So one can perform different amount of token dropping for different images, whatever one likes. One can schedule the token dropping. And then after that, rather than trying to concatenate images onto the batch dimension, one creates a single sequence out of all its images and hands them all simultaneously to the transformer. Inside the transformer, one needs to make sure that images don't attend to each other. That's straightforward. And then pool the representations appropriately to predict whatever you're trying to predict, either at training or test time. So this we call patch and pack for vision transformers. There's a PR to make it available till recently in Hugging Face or Tim. So people can try that if they want to. So this removes a lot of the limitations from the traditional pre-processing pipeline. You can keep your original aspect ratio, you can process large images, you can process small images, doesn't matter. You can perform arbitrary image-dependent pre-processing because they don't have to end up as the same sequence length. And you can choose your sequence length independently of other model parameters like the patch size or the number of pixels in the image. And so this results in has two consequences. You can train more efficiently and you end up with a more general model. I would add that this is not the only way to end up with a more flexible model. You can also make the architecture more flexible, for example, by having a variable resolution patching operation on input. So let's look at the results of training efficiency. So again, we train these models, pre-train these models on a large number of images, and we found that both on transfer and pre-training accuracy, that the navit, that's orange, so the orange points are what we call native fit, because it's trained on images in their native resolution, trains 4 to 5 times faster than the equivalent fixed resolution vision transformer, which is a very large saving when one's training these big models. So to dive a little bit in more detail as to where this saving is coming from and also the flexibility aspect, we can look a bit at different resolution evaluations. So what Navit allows one to do is combine the best of low resolution and high resolution training. If one's training with fixed resolution, then the advantage of low resolution training is that one sees more images, and seeing more data is generally better. The advantage of high resolution training is it allows one to evaluate on high resolution images. So evaluating on high resolution images generally performs better. But if you haven't seen any high resolution images in pre-training, one will have some penalty for going out of distribution. And so in this plot, what we show is evaluating standard fit models and Navit models at different resolutions. So each panel represents a different evaluation resolution. And on the x-axis, we have models trained at different maximum resolutions. So for the VIT models, the x-axis corresponds to the only training resolution. For the Navit models, we train on all resolutions up to the point on the x-axis. So it's the largest resolution that the models see. So if we look, for example, at the 224 res eval panel, then the pink arrow just indicates the eval resolution. We can see that the VIT model is trained at the eval resolution is working quite well. But if we move to smaller or larger images, the performance tails off very quickly. The Navit model performs much better when evaluated on smaller images. It's seen smaller images during training. But interestingly, it also performs better when evaluated on larger images. Even though it hasn't seen larger images during training, the fact that it's seen images of multiple different resolutions allows it to generalize a bit better. And so if we sweep across all evaluation resolutions and pick the best eval setting per model, we can see that the native model is always performing better, and a particularly high resolution is performing much better than the fixed resolution model, because at those high resolutions, it's seen a few high resolution images, but also plenty of low resolution images. So it's seen a requisite large number of images, whereas the VIT model hasn't been able to because it's only been trained on that one resolution. This means that at test time, one can reduce the resolution to trade off inference speed and accuracy. If one tries to do that with a standard bit, then performance will degrade very quickly. But with the NavIt, one can reduce the resolution, get a faster model if that suits the application, and retain high accuracy for a longer period. I'd like to also make one quick note on efficiency regarding NavIt. So those who are looking carefully will have spotted that some computation inside the architecture during training is masked. So because we create these sequences, then, and you don't want images to attend to each other, then you mask that computation, which is bad. So how much of a problem is it? Well, what we see is that for modest sequence length, so anything less than 2,000 tokens, and very few vision transformers are trained on more than 2,000 tokens, the self-attention layer itself is actually a relatively cheap component of the architecture. Asymptotically, of course, it's expensive, but it's cheap at this scale. So for example, if we have a medium to large model with a 4K model dimension, we pack 4 examples per sequence, then we get around about a 5% overhead due to this masking. But we saw earlier that it was about 4 times cheaper to train, and that's including this 5% overhead. So it's a relatively small penalty compared to the advantage one can get. So this improvement in preprocessing allows one to train dense models faster, but dense models still have a limitation when they scale, that every parameter you add adds in proportion some training and inference cost. In this work, we seek to address this with mixture of experts models. So mixture of experts models have been around for several years now, and they have this wonderful property that one can add parameters to the model without changing the cost, training or inference cost. Because the idea is that every token or every patch in the case of vision in the MLP layers is routed to 1 or 2 of n experts. These are just MLPs with separate parameters. And what this means is you can add more and more of these expert parameters, but because it's sparse, you don't change at all the inference cost. So cost and capacity are completely decoupled in these layers. However, there's a number of issues with the well-established sparse MOE recipe. The first is that the fundamental issue arises from the fact that you have to make these hard routing decisions as to which parameters to descend each token to. And it's difficult to train these discrete decisions with backpropagation. This results in kind of practical challenges when it comes to training these models. What one easily ends up with is with some experts being overutilized and some underutilized. You have tokens therefore being dropped, some experts not being used at all. And so what one typically does is construct various auxiliary losses in order to encourage load balance. This works, but it's quite finicky to make it work. And what's been found empirically is that often a random routing strategy can do as well as this learned routing strategies, which certainly feels suboptimal and as if one is not using the capacity of these MLE models as well as one could be. So the idea behind the soft mixture of experts model is to replace this hard assignment with a soft assignment. So one can redraw the MOE architecture like the diagram on the left, where one considers that one has n slots associated to each expert MLP, and one performs a discrete assignment between slots and patches in the image or tokens in one's centers. And one learns this discrete matching between slots and tokens. Now with this view, one can, it's a very simple generalization to say, well, instead of performing a discrete assignment, we will perform a weighted average. So every slot will be filled with a weighted average of all the patches or all the words. Therefore, each expert will process each slot. Each expert is assigned a fixed set of slots, but each slot is a weighted combination of all the patches. Then after the expert processes the slots, the patches are then distributed, the slots are then distributed back to their original patches. So it's sort of unweighted on the output. So if one does this, one retains the nice property of a sparse MOE that one has this sparse assignment of slots to experts. So one can keep adding experts, and as long as one's number of slots remains fixed, one's total cost of the layer remains fixed. And so one can decouple cost and capacity as for a sparse mixture of expert. But now the model is fully differentiable. Gradients can flow through the experts, through this soft assignment, and to the router. And this means that it's much easier to train. The model is balanced by construction, so it's not possible to have underutilized experts or any kind of token dropping, and you don't need any auxiliary losses. Finally, and this is maybe a detail, but it's an important detail, if you train a sparse mixture of experts and an expert goes out of capacity, then some tokens from some images can get preempted, so they don't get processed. So you have some kind of non-determinism across your batch. Whereas with the soft mixture experts, you don't have this property. You can't have one image preempting the tokens from another image. So the architecture diagram looks like this. I won't walk through it here. I'll just flash the slide up. You can look at the paper for more details on how this mixing layer is done. But just to note that it's not an attention layer, but it looks a little bit like an attention layer that performs this soft dispatch of tokens and slots, and then this soft combine of slots and tokens. I have to talk about this more afterwards. So how does the soft mixture experts work? So these are the training Pareto frontiers. And the first thing I'll highlight is that on the x-axis, we have actual training time. We use TPUs, but it could also be GPUs. And there's a lot of fantastic work in sparsity, but it's often hard to make this work realize the benefits on GPUs or TPUs due to the challenges in implementing some algorithms. But the soft mixture experts actually works nicely on today's hardware. And what we can see is that the dense vision transformer in red is the baseline. The orange and green are two flavors of sparse mixture of experts, and they're a little bit better than the vision transformer, but not a lot. But then the soft mixture of experts is substantially better at all scales from small up to large. So this is nice that the soft MOE trains faster than sparse MOEs or dense transformers. But actually what it's really good for is for inference, because you have this very large model, but it's sparsely activated, so it can be fast in inference. So we train some soft MOEs for about the same amount of time or a little bit less time than their equivalent dense vision transformers. And we find that depending on the evaluation, either the model's better than all the dense models, or it's 5 or more times faster at inference time compared to dense transformer. And this is something that we're really excited about. So why does it work? It's hard to answer that precisely, but something that we've noticed that's a nice property that seems to correlate with good performance is the ability to use lots of experts. So I'll take you through this diagram that shows that. So each of these heat maps shows a different model. Well, many different models, each square is a different model. You have the soft mixture of experts models on the left and two flavors of sparse mixture of experts models on the right. And the lighter color denotes a higher accuracy model. Now, on the rows, you have different number of slots. So as you go down the rows, you have essentially more tokens in the experts layer, or more tokens being processed per expert. And so the models get more expensive in terms of flops as you go down the rows. And one can see this if one looks at the speed. So the bottom heat map to speed, as you go down the rows, these stripes indicate that the model's getting slower as you add more slots or process more tokens per expert in the sparse MOE case. However, the columns indicate the number of experts. So as you go across the columns, the capacity is getting larger, but theoretically, the number of flops should stay roughly constant. What we can see in the soft mixture of experts case is that for every model cost, the best model is the one with the most experts. And this is what one might hope, that adding more experts shouldn't hurt. It should only help to add more parameters, even if one doesn't increase the number of flocks. However, as we've observed with sparse mixture experts in vision and in language, there's some sweet spot. There's some point at which where adding more parameters makes the model harder to train and therefore outweighs the benefit of having a bigger model. We can also see that as we add more experts, we have only these dense operations, so throughput doesn't suffer too much. Whereas with the sparse case, your throughput does suffer more as you have to do these discrete assignments as you have more and more experts. So these are two really nice properties of the soft approach to mixture of experts models. So this concludes some of our recent work in training vision models and their use in VLMs. So
welcome to ICCV'23. We are sorry for this queue and we thank you for your patience.
Well done for getting in before the queue and welcome to ICCV. So I will wrap up. We presented the VID22B and studied some of the properties of scaling up vision models, and then been working on some techniques that presented the native VID and soft mixer experts in order to scale more efficiently using the existing hardware. So thanks very much to our team and thanks very much for listening.
Hello. Yeah. Thanks, Neil. Thanks for the great talk. So we have around 5 minutes for questions. Please raise your hand if you have a question. We'll try to get it. And the next speaker can already come up here and we can set it up. It's Maria Attarian.
Hi, that's the fantastic. I have one question about that software.
I think it's, do you have the Zoom link? That's great. That bigger? That's smaller. Yeah, no. So it's a good topic.
But maybe some of them clarifies and robotics person, so more than a minute class. So like I'm not going to go to some technical, but I don't want to go at high level where we're at using
I said that about robotics because finally people are applying this robotics. It's good.
So this is something like how we're using them, and then like interesting directions that I see.
And then this is still up to date, right? I'm gonna make just introduce.
Yes, we're Google DeepMind now.
Oh yeah. Great.
But
you can already try to join the audio.
Then you use that to get the weights, and then average the weights, and then on output, you
press this
on average according to that same set of weights.
Thank you.
Seems possible.
Any other questions?
So
yeah, once we're yeah, use my from different networking software. Yeah, we'll see. Otherwise, I'll leave my laptop.
yes, a little bit. So this is something I would talk with especially this question. if one looks for it, then for sure one can find specialist expectation indexes. I think you can't one all the processes practice with the eyes, but it's certainly not the case that every expert is super interpretable and we can see exactly the decomposition is happening. So one does see some using nice interpretable experts, I think it's for example some appendix. But you have to look a little bit for these.
Okay, thanks. Yeah.
Go to Zoom.
Hello? Can Zoom hear me?
Perfect. And now you can go back to this one. All right, great. Let me quickly. All right, thanks for the great questions. Thanks again for the amazing talk here. Now it's my pleasure to introduce Maria Attarian. She's a robotics research engineer in Google Brain DeepMind and a PhD student at the University of Toronto. And her focus is on visual imitation learning in robotics and methods that attempt to apply continual and adaptive learning in robotics manipulation. Thanks for coming, and the stage is yours.
Hi, my name is Maria. Thank you for the introduction, Yuki, and thank you for having me here. It's a pleasure to be here. As mentioned, my focus is robotics, and I know this is a vision conference. So I'm going to give a high-level overview of how we use these models in robotics right now. Is it not? No.
Sorry. No, I forgot.
Thank you. Sorry about that. Yeah, so hopefully I'm going to be giving you a high-level overview of how we use these models right now in robotics and what some of the gaps are and some hopefully cool directions for the future, at least the way I see them. All right, first of all, how do we teach robots how to act in the world? One thing that you will hear a few times during this talk is policy learning. And for those of you who already know what policy learning is, bear with me, but just like quickly to introduce for people that are not familiar with the terminology, it's simply just learning a function that maps observations and possibly goals to actions. So for instance, in this little simple example, if your state, if your visual state is like a cupboard and your goal is open the cupboard, the policy is just a function, a learn function that spits out actions that a robot can execute, and hopefully your resulting visual observation will be an open cupboard. Now, how do we teach a robot what it can do, what actions it can do, and learn how to use its body? So one natural thing we could do is learn from random trajectories and learning through play. So basically what that means is we gather data of just the robot being allowed to explore and discover what it can do with its body. If you come to think about it, this is similar to how humans learn, how we learn as babies, we play. And we kind of learn how to use our hands and feet. And the downside of this, of course, is that we don't really end up learning useful things, as in like things that make us do useful things in the world. And humans we do have intrinsic motivations that eventually get us to learn how to do things that are useful to us. but robots, not so much. So that brings us to how do we teach robots how to move with intention? And that brings us to imitation learning. Humans are very good imitators. So what we do with imitation learning is we collect trajectories that represent what was the state of the environment before the robot executed an action, the action that was performed to complete a task, and what the resulting state of that environment was. This can be a powerful supervision for imitation learning. So basically just supervised learning on take in state, output action, make sure that you output the right one or close to the right one, or even to learn a dynamics model through reinforcement learning. All of these approaches have shown promise, but yet the tasks that we are currently solving are relatively simple still. So if you look at the big robotics papers right now that have created a buzz, at least I can, like the Google ones are the top of mind. Like RT1, RT2 is going to be presented at Coral this year. The tasks are kind of a similar manner, like pick and place, remove objects near some other objects, etc. So, long story short, we have a long way to go still. Now, off to how we use these large models that we're here to talk about as world modelers and planners. First of all, why reasoning and planning is hard. Let's start with looking at language models. So LLMs encapsulate a lot of a priori knowledge about the world. They seem to bake it in there, and that makes them a natural thing to choose for roboticists if we want to plan into steps for robots. So think about it, if we have a large language model that can spit off that can take in a high level task instruction, split it off into steps. And if you have a good language condition policy that takes in those steps, you should be expecting to get something good on the other side. Okay, so I'll return back to the slide, but before I do this, this is a video. So this is possibly one of my favorite snippets of,
Actually, let me try this one.
Okay. Yeah, it doesn't show up.
Were we? Sorry.
Yes.
Oh, I see. Okay.
Can I?
Didn't.
No. Okay.
Yeah.
Okay. Okay. Yeah. Before. Yes. I guess. Hopefully.
The mouse is here. So.
Okay. So this is, well, if it plays, this is a snippet from one of my possibly favorite videos on YouTube that showcases a dad that is given instructions from his kids on a piece of paper on how to make a peanut butter and jelly sandwich. So this is going to be.
Is the link here? All right.
This is the full video.
Oh, that's a different video?
This is the full video. I just like cut a little snippet out of it. Okay.
Where it is? Roughly?
Yeah, it's just like we can play it like first few seconds.
Okay.
If we can.
See.
If not, I can just describe it.
Yeah.
It's okay, I can just describe it. So basically this little snippet, if it were to play, it would show a dad given instructions by his kids in a piece of paper on how to make a peanut butter and jelly sandwich. And it is astounding how many things are implied when we are given instructions. we somehow have all this a priori. There we go. Okay, I'm gonna go back here. Okay, yeah. So basically you'll see a dad and he's being told like, okay, take some peanut butter and spread it all over 2 pieces of toast. And he just does as he's told, and he's like taking this peanut butter jar and just like taking it all around a bread because, well, he wasn't told like unscrew it, put the knife in, take some peanut butter out of it, then lather it. So this is kind of like implied steps that we already have in our heads, built as world priors, because we kind of know how things work. So this is a level of knowledge that robots don't a priori have, and this is something that we have to bake in. So that would have shown us, and you can look up the video. You can just Google it; it'll pop up. This would have shown us that what humans consider a good set of instructions to complete a task allows for a lot of abstraction. So many details can be omitted, and still humans can fill in the blanks, and that's pretty amazing. Because coming from a robotics background, this is like so not something we can do with robots. So we are very good at building priors throughout our lives about how language maps to physical concepts, as well as how physics work in general. And the best, and even if you have the best language condition policy right now for robots, like they can't do even more basic things that are told to do explicitly perfectly yet, let alone make implicit assumptions about things. So basically, what we have right now, like why though an LLM alone is not enough to plan for robotics well? It is lacking visual grounding. An LLM does not know what the current state of the world is, what actions are available to take, or what the result of said actions would be. And this is a good example, for instance. It's a small, simple one. But basically, like, if I'm not given instructions and I can't give back feedback to a large language model, I can't really make an omelet with this response. Okay. I'll skip this video. All right. Let's move on to planning with a VLM, which kind of bridges that gap where vision grounding now exists. As roboticists, we want both, so we are excited to be looking at multimodality. Of course, these VLMs do not output actions, but using them as backbones to encode visual language as input for policy learning has been an exciting avenue for us, because of course, they incorporate so much knowledge about the world that like it's only natural to try that. Why is this not as easy though for robotics? Well, data for robotics is not as easy or as cheap to come by, and each lab, believe it or not, is focusing on its own embodiment, and embodiments can differ a lot from one another. So yes, unfortunately, we are lacking a little bit of standardization still, which is an inhibitor factor. And of course, these models still don't have any notion of physical laws or how physics work, because it's just vision and just language. A natural next step for us that, of course, we have been playing around with is combine this vision plus language concoction and make it predict actions. So we're training them in such a way that we're encoding actions in like tokenized fashion or other kind of representations, and we're expecting we're tailoring these models to predict actions at the other side. Nothing still encodes physical constraints or what we humans call common sense. All of those implied nuance that we take as given, these are not encoded explicitly in there. But we have had some success already with mostly limited generalization to new tasks. Sadly, environments can vary a lot visually. So this is a kitchen and that is a kitchen and that is a kitchen, but it looks very different in pixel space. And also even how objects are meant to interact with can vary a lot. So for instance, you can get a fridge that your motion looks like this, or you can have a fridge that your motion looks like this. And that for a robot is quite different. Also, robot embodiments, as I mentioned earlier, can differ a lot. So these are miniature models of different robots, and their controllers are quite different. And then if you add on top of that different end effectors with different number of fingers and degrees of freedom, then your action space can kind of explode and add even more complication to the task of learning how to do things in the world. Why is a perfect planner not enough though? Because even if we had a perfect planner, it wouldn't be enough. Policy learning is hard, even with a perfect planner. So let's overview the gaps real quick. Adaptation to changing dynamics. So in your space, you move, objects move, things drop. It's an ever-changing environment that a robot needs to be able to adapt. So any model we have needs to be able to adapt. Error recovery, a lot of the policies we learn right now are not very good at addressing the error propagation problem or recover from errors, but they are very good at making them. Safety. Safety is, of course, imperative for you and your robot. Generalization to new tasks and environments. As I mentioned, current approaches have shown a little bit of success there already, but they don't go too far off the training distribution of tasks and environments. And lastly, one thing that I'm mostly excited about is generation of novel motions. So if you have a task that should be solved in a similar motion as some other task that you know how to do, this we have not, or a task that you can compose different actions that you know how to do to complete, we're not there yet. So what's next? I'm going to talk about some cool ideas the way I see them, and hopefully you're going to find them interesting as well. So first of all, of course, improving planning abilities, because even that can take us a long way. So make VLMs better at planning. How do we do that? We can cast the planning problem into a VQA problem. So every step of the way can ask, did this instruction get executed properly? Yes, no. If yes, continue on. If no, replan. If something like this could be used as a reward function, for instance, for RL fine-tuning or some other way of addressing compound errors and error recovery. Of course, we can fine-tune and collect more curated data with language instructions and visual observations that are more granular or step-by-step, and fine-tune using those so that we have a model that is more tailored to doing planning for what we need in robotics. And of course, combine the two, because why wouldn't you? Another direction that I'm even more excited about is actually baking those world priors that we have in our heads, but into a robotic brain. So there has been recent work that they're trying to hallucinate through diffusion models a full video of the robot doing a task and use this for supervision for policy training. That's cool. I would say maybe it's not necessary to have a full video to be able to do a task, but encoding things that we as humans consider implied or common sense could help. So for instance here, if somebody tells a human, oh, please swipe the table, it's kind of implied that you don't want the crumbs to end up on the floor, but a robot wouldn't do that, wouldn't know that. So also we could think of, so yeah, as I said, encode laws of physical world. One thing that has been interesting in the language world is chain of thought. So we could apply chain of thought techniques or come up with new ones to encode common sense that way, or even what is physically possible in the world of a robot, because physical constraints do matter a lot for robotics. Or even explicitly encode physical laws through fine-tuning again. Although something like this would probably need a curated data set that would need quite a bit of effort. And to be honest, I'm not too sure how it would look like. Lastly, this is the most exciting direction for me at least, skill and action spaces. How about we take a closer look at the connection between skills and action spaces? So skill learning through an action-centric perspective, basically. If you think of different skills and the way you do different things in the world, skills can be categorized based on the motion you need to complete them. So for instance, if you open a fridge and open a cupboard, you have the same motion, but in pixel space, these things would look very different. So naturally, a model that is just trained on like language and vision alone would see these tasks and be like, oh, these are completely different. I don't know what to do. So how about we categorize and bundle tasks based on the motion you need to do to complete them? Then hopefully that would make a new similarity metric emerge, and we'd be able to recognize a similarity no matter what I'm opening or picking up or anything like that. So then you just encode the task, see where it falls into this latent space of tasks, see how close it is in proximity in other tasks, and if you know how to do something close by, well, that's a good place to start. So this is a good example. I mentioned it briefly. If a robot is asked to open a fridge, well, if it doesn't know how to open a fridge, but it knows how to open a cupboard, well, okay, that's a good place to start to try that. In summary, one day we will have robots, hopefully, that will be able to make a peanut butter sandwich for us. But until then, we do have a lot of ways to go and a lot of exciting work to do. Thank you very much.
Thank you for your great talk. Now again, we move to the questions, and for the people standing at the back and the sides, there's actually some seats at the front, so if you can just come to the front, don't be shy. There's enough space here. All right, who has questions? Oh, and the next speaker. Questions? Okay, then I have a question. So, especially for the wildfires physical laws, any indication about this, how you might include them in these settings, which basically just throw data at them, right? And they learn from the correlations of physical laws or about laws, basically. So.
Yeah, so basically, the first thing that we could do is start encoding constraints more explicitly of what a kinematics chain of the robot can do, so that we try to limit essentially and flip or constrain the output of our models that output actions to things that are even feasible for our robot, so that we don't end up with actions that are completely bogus or might get the robot to an unsafe position. So how to encode kinematics chains is not necessarily a straightforward thing. I know of works that have tried to do this with just encoding basically config files. You could do this implicitly by just, I don't know, encoding kind of like different, we've done it before with like encoding different grasps and looking at where the contact points lie. So that's kind of like an implicit way of doing this. But basically, yeah, I would say start from like ways to encode the kinematic chain rather than arm.
Right. Yeah, thanks. Any other questions? Yes. Yeah, thank you for the great talk. I have more of an opinion question. So you mentioned that like there are mainly two way of thoughts about constructing world models. So first is like notice everything implicitly, and second is move more towards like more symbolic representation of the world. And for example, in your example with the copper and the bridge, yeah, they look differently.
to try to bridge that gap and learn skills in simulation, like policies essentially in simulation that will port over the real directly. We are bridging that gap. It's not perfect usually. It doesn't port over that well. There's other works that try to learn like center real policies in RL and then try to put them over in real as well. But yeah, basically the gap is still there. We're bridging it, but it's still there. Also, even in simulation, you still need a lot of data.
Hello, everyone. So let's welcome our next speaker, Samir Gadre. So Samir is a fourth-year PhD student at Columbia University, working with Shuan Song and Lulu Wishbi. His work are about large-scale dataset construction and large-scale model training, including the famous model soups, data comps, and open flamingo. And let's welcome Samir.
Hello. So yeah, I'm not Ludwig. Ludwig unfortunately came down with a sore throat this morning, so I'm kind of filling in here for him. So these are his slides. Yeah, so. Okay, so state-of-the-art kind of pipelines for creating really good models often follow like two steps. So the first is this pre-training step. So here we're going to have some kind of a large noisy data set and some kind of a general objective, such as predicting the next token in an NLP context or aligning images and text together in a kind of like clip contrastive way, which we might be used to in Vision. And this is really nice because we're going to learn all kinds of general things about our data. And then in the second step, what we're actually going to do is we're going to create these much smaller data sets and use them in order to adapt these very generic models to do really well on our specific tasks. So the left part of this diagram we call pre-training, and then right is fine-tuning. And specifically, we're going to say that the model that has been pre-trained can do certain tasks zero-shot. So here what we mean is that it's able to do these tasks, at least to some degree, even without the fine-tuning step. So one question that we might have is, what is sort of the correct way to fine-tune a very, very large model? So today we're going to look at this question from many different aspects, but we're going to pay special attention to this thing called out-of-distribution robustness. So here what we're going to do is once we fine-tune the model on our target data set, we're actually going to evaluate it on some data sets that are similar to our target data set, but have slight shifts. So one example here is maybe we've trained on really nice clean images, but we want to test on images with rain appearing. And this is maybe a very realistic scenario for self-driving car applications. Here you can also imagine in the healthcare industry, we might have a test set, but microscopes might be a little bit different, and say the focal length is a little bit different. We still want our model to work on these kind of these distribution shifts. And we can imagine other kinds of distribution shifts as well, some appearing in robotics related to the environment or to lighting conditions, or to chat assistants wherein different people are kind of speaking in different ways or prompting these models in different ways. And really what we're getting at here with out of distribution robustness is a proxy for reliable machine learning and methods that work in many, many different scenarios. So as a case study on this, we're actually first going to look at ImageNet. So ImageNet has had a lot of staying power in the computer vision community. It's been around for a really, really long time. But we might ask the question, since the test set has also been around for a long time, maybe people are starting to overfit to this test set. So what we might do, and what people in the community have done, is create new test sets for ImageNet to make sure that we haven't overfit to ImageNet. And the idea here is that ImageNet, we care about ImageNet, but what we really want is for these models to be very performant on a wide range of ImageNet-like images. Okay, so what happens here when we collect a new test set? So on the x-axis, we have the performance of these models on the original ImageNet test set. And then on the y-axis, we have this recollected test set called ImageNet v2. And what we can do now is we can plot the accuracies or plot each of these points on this plot here. And what we notice is kind of a predictable gap between ImageNet accuracy and ImageNet v2 accuracy, with this dashed line being y equals x, or perfect like robustness across this shift. So this is kind of interesting. We might ask, like, why is this happening? So here again, we see that these models follow a very nice predictable trend. So now we're going to look at a quantity called effective robustness. And what this basically is how far can we get off of this predictable trend line? And the really interesting thing is that humans are more closely on this y equals x line. So if you were to take a person and ask them to do the ImageNet classification test on the original test set and on this V2 test set, they would get approximately the same accuracy. That's what this is saying. Okay, so here we have many more models. And one interesting thing here is if you turn your attention to the top right of this plot, you have these green points. And these seem to be a little bit off the line, as we can see. And the only real difference between these points and some of the other points is that they were trained on more data. So one hypothesis you might have based on this plot is that more data is good in terms of models being effectively robust. Yeah, and these are fairly massive test sets or training sets. Okay. So this was sort of the state of things circa like 2019. And then this clip paper came out that kind of changed this whole field of robustness and how we might think about robustness. So yeah, when this came out, it sort of smashed a lot of the existing work on effective robustness. Here you can see like huge gains across all of these different test sets. And this is very interesting. Ludwig certainly finds this interesting, and I do as well. And so a lot of work in his group in the past few years has gone into trying to understand why are these clip models so robust here compared to those standard models on that trend line. Yeah. So yeah, so this is a plot from the clip paper, kind of showing this very thing. So these purple points here are sorry. So the orange points are the zero-shot clip models. So these are kind of the clip models out of the box. And you can see here they're way more effectively robust than this blue trend line. But one interesting thing is that when you fine-tune a clip model, it gets you to this red trend line. So what we can take away from this is that the process of fine-tuning, the second step in our recipe from way earlier, actually hurts the robustness of a model to this distribution shift. And so we might ask the question, how can we actually get the best of both worlds? These clip models are incredibly robust. We'd like to preserve this robustness while also getting the accuracy gain on our downstream task, in this case, ImageNet. Okay, so this work led by Alex starts trying to get into first understanding why clip is robust in the first place. So you could hypothesize that there are many potential reasons for this. And here we have a few. So first of all, we have language supervision. So clip uses sort of a different objective than the standard image classification objective. And we might hypothesize that this is the reason why it's so robust. It could also be due to the training data. Recall from earlier, those green points were a little bit more effectively robust, and largely they were also trained on more data. Training set size is another potential factor. And then this loss function as well, which is sort of related to the language supervision. Okay, and then a couple more points just related to prompting and how you might try to construct a zero-shot classifier in clip world, and also model architectures with the most performant clip models using a VIT architecture. So what Alex essentially defines in this paper is that none of these other things really seem to matter when kind of controlling for them one by one, but the training distribution does seem to matter. And for specific details, I'll reference you or point you all to the paper. But this is kind of the key takeaway, is that the data really here matters quite a bit. And based on this, we actually had a large project called DataComp, where the idea is, instead of iterating on model design, what you do is you actually iterate on dataset curation. We know that data is incredibly important. And so the point of this competition is to kind of encourage the community to think about how we curate our data sets. And actually, we have a workshop tomorrow, so a bunch of fabulous speakers, and I would encourage you all to come out and say hello. Okay, so now we're going to turn our attention to that second step of our pipeline. So now we've talked a little bit about pre-training. We know that there's some benefits to doing this in terms of robustness, but we really want a state-of-the-art ImageNet model, right? Or we want to be really, really good at a downstream task. So now we're going to ask the question, can we actually get the best of both worlds? Can we be really, really robust to distribution shifts while still having amazing performance on our downstream tasks? And this is work led by Mitchell Wartzman and Gabriel Vilharco. Okay, so going back to kind of our plots from before, x-axis again is performance on, say, ImageNet, and then y-axis performance on, say, ImageNet v2. We find that in the schematic, right, when we fine-tune a clip model, we get much better at ImageNet, say, but we've lost our robustness, and we deteriorate as far as, say, ImageNet v2 goes. So this should kind of orient. So we have kind of this trade-off, right? So the original clip model is very robust, but it lacks performance on, say, ImageNet, whereas the fine-tuned model, we see the reverse trend. But really what we want is a model that is good at both, or has both of these properties. And so what Mitchell and Gabriel found in this paper is that a very maybe now in retrospect obvious thing, but at the time not obvious thing to do is actually just take the weights of these two neural networks and just add and divide by 2. And so this is what we'll call y is ft. and it builds on a lot of prior work. So they didn't come up with it out of nowhere, but the idea here actually, so this is like seemingly magical. It doesn't seem like it should work. It seems like kind of a nonsensical thing. There are lots of non-linearities in a neural network. Maybe if you say like averaging 2 linear layers, that makes a little bit of sense. But the whole network, that seems a little bit far-fetched. But there is actually some intuition in the literature about this. So this Frankel et al. Paper looks at what's known as linear mode connectivity. So this is a phenomenon wherein 2 solutions actually lie in the same basin. So the observation here is that if you start from the same initialization and train on data with 2 different seeds, you actually land up in 2 different basins. And the interpolation between these final solutions, here theta 1 and theta 2, actually lie outside of this basin, right? But if you, if you do the following, if you share part of the training trajectory from theta 0, and then branch off later during training, these solutions are actually connected or lie in the same basin. So that kind of gives us an intuition for why this WiseFT thing might work. Because you can think of clip training as a lot of shared trajectory during training, and then fine-tuning as this small little branching at the very end. And so because of this, you're probably still in the same basin as long as your learning rate is like reasonably low. And that's why, or that's at least the intuition why this kind of weight averaging thing makes a little bit of sense. As far as for like why it works or why it gives performance boosts, this schematic kind of is meant to illustrate that the fine-tuned models here shown with a square and a diamond usually don't achieve the lowest possible ImageNet test error. So here you can think that you have some training distribution that you fit on ImageNet train, and your models are maybe a little bit overfit to the training distribution, but really the validation set or the ImageNet test set is slightly different. And so maybe you're learning things about the train set that don't necessarily transfer. Okay, so this is essentially WiseFT in a schematic. So what we're going to do here is we're going to have this interpolation factor alpha and take this kind of like convex combination of the zero-shot model and the fine-tuned model. And interestingly, we get this blue point or this cyan point. And this point here has the exact same accuracy on the in-distribution task, so on ImageNet, say, but you can see there's a large jump in the out-of-distribution robustness. So we're kind of getting robustness for free, should be the takeaway here. Okay, and now we're going into real data. So the gain is actually substantial. So we're getting this model that gets above 86% on ImageNet, but with this WiseFT method, we can get up to like around 9 percentage points on our distribution shits, which basically comes for free. And Mitchell and Gabriel did an amazing job in this paper evaluating on many different test sets and did quite well in terms of all of these out of distribution benchmarks. Yeah, and I'd refer you to the paper for the specific details there. Okay, one other kind of nice finding from this work is that you can actually do a lot of these experiments at small scale. So because we have put models with many different zero-shot accuracies, we can actually experiment with the sort of worst models. And usually, like what happens, what we found in these cases, or in this kind of regime, is that the stuff from the smaller scales actually like tends to transfer quite well. So yeah, doing YZT at kind of smaller scales was kind of helpful. Okay. Okay, and then yeah, there's been a bunch of other kind of really nice follow-up work related to YZT and like kind of looking at this effective robustness. Okay, so now you might think like averaging models seems to work, so like that's really cool. But why stop at 2 models? Can we actually do this with many different models? So now going kind of back to the traditional fine-tuning recipe, what people usually do is they'll choose a bunch of different hyperparameters when fine-tuning. It's not really known which ones will yield the best results. So we try all of them, and then we evaluate on a validation set and pick sort of the best model, right? And so that's maybe this model here. But in model soups, what we did is it's kind of a similar story. Instead of just averaging or choosing the best model, let's just average all of the fine-tuned models together. And this actually, we'll call this a model soup, and it's very similar to this averaging of 2 models, but now we have n models, and we call this kind of a uniform soup. And we find that this works with reasonable like learning rates for fine-tuning. So yeah, and then this method was able to produce a SOTA model on ImageNet, which is kind of nice. Okay, and then in follow-up work, we also asked the question, like, we fine-tuned now on a single task, and we've averaged the models together, and this works nicely, but can we actually fine-tune on different tasks and average those models together? What happens? So this is this patching work, and it turns out there also you can kind of fine-tune on many different tasks, average together, and kind of get these gains for in the multi-class setting, without necessarily hurting performance on tasks where CLIP is already performing. Okay, so this is a conclusion slide. Yeah, so the key takeaway here is that we're adapting these models by fine-tuning them, but we should maybe even think about how the initialization can be useful in order to improve these kind of like robust quantities. Yeah, and that's it for me. Oh yeah, these work.
Thanks for your talk. Thanks, Ludwig. Samir.
Yeah, thanks, Ludwig.
All right, so any questions? And just to note, there will be questions. We have around 10 minutes, then there will be a coffee break, and then we'll continue with the next half of the session at 11 a.m. All right, questions? Yes.
Great. Yeah, thank you for a great talk. Could you elaborate a little bit more on like what it means for fine-tuning? Like just fine-tune all the ways, or some kind of fine-tuning on the subset or something lower?
Yeah, so in this word fine-tuning, we fine-tune all of the weights. Yeah, so end-to-end fine-tuning. One key here is that you want to fine-tune with like reasonable like fine-tuning type learning rates. So you don't want to use like say a pre-training learning rate that's too high, because what that tends to do is it pushes your fine-tuned solution out of this basin. So we think about this like kind of linearly mode connected basin. If you fine-tune with a learning rate that's way too high, it pops you out, and then you get a solution that is not compatible with the other ones. But yeah, surprisingly, nothing like other than learning rate, I think nothing like too special. And even there, like you shouldn't really fine-tune with a lot or like too high a learning rate anyways. So yeah.
Like for the next question, people leaving you be quiet. Thanks. Well, I have 2 questions. The first one is for models. Since you
you have more than two. For this many models, like how do you find the complex combination? Like you do it manually, or there's some different time fitting, or any other methods that you use? And that's my first question. My second question is, have you find like if there's a benefit for different kinds of combination for different layers, or is it always true that I'll just have this specific alpha parameter for this entire model?
Sure. Yeah. So for the first question in the model soups paper, we look at a few different variants of the algorithm. The first is a uniform soup. So here what you do is like all of the models that you fine-tuned, you have this 1/n parameter, or 1/n factor, where n is the number of models, so you take like kind of a uniform blending of them. There's also the greedy soup, which tends to be a little bit better in distribution, but I believe loses a little bit of like robustness. And here what you do is you have like a validation set, and you only include the ingredient, the fine-tuned model, basically, if it improves the performance on the validation set. Yeah, so in model soups, we don't really look at like taking more complicated averages between models. And then to answer your second question, it is highly likely that there's more that you can do here. So like you maybe don't want to just have a standard alpha parameter for all of the weights. People in Colin Raffles' group have looked at this a little bit, and I think they do something by using like Fisher information in order to like select the parameter or the mixing coefficients. I want to say per parameter, and they show that it does improve over, but like yeah, I'll refer you to the paper so that you can like look at the exact numbers. But yeah, there are probably other things you can do. Yeah, sure.
So I imagine the result for education or you have any prediction? The same kind of method work for like education or
Yeah, I know that there have been some models post this work. Like I want to say the Pali model uses like a model soup towards the end, and yeah. So I think to answer the question, like I think that the souping part, it's worth trying. Yeah, it's worth trying for like segmentation or bounding box detection. Maybe this already exists and I don't know about it, but I think it's reasonable. It's a reasonable thing to try.
I'm seeing sort of a similarity between model souping and also federated learning. So why don't we see the same benefits in federated learning? I think you maybe see that we don't have strong pre-trained models, but
yeah. Sorry, I'm not like so familiar with federated learning, but yeah. So I think one key for at least the YZFT thing is that your initialization is really good. And I guess you were kind of alluding to that in your question. Like Clip is already really pretty good at ImageNet. And so, yeah, if you don't have like a nice initialization, then maybe there are less benefits to doing a YZFT type thing. Yeah.
all right, we have time for one last question. Oh, okay. Is the result of the soup better than the ensemble?
No, so yeah, so in general, the ensemble is still outperforms the soup. So in the model soups paper, we have kind of some theory as to why this is and why we think that the model soup actually approximates the ensemble. So I think, yeah, this is in the appendix of the model soups paper. The one thing to note though is that the ensembles are like really expensive, right? So like for a lot of for that paper, I think there was something like 72 different models that we ended up souping. and for a lot of the experiments. And so like, yeah, you wouldn't necessarily want to run 72 models in parallel. Yeah, but that's a good question.
All right, great. Let's thank Samir again for all the experts. You know, conference, like earlier you can see,
Hello. Hello.
One more minute, so if you can start sitting down slowly, please. All right, let's get started. So now we have Ishan Misra, who is at Meta AI and working on generative AI and the Gen AI team with his talk about self-supervised learning for scaling to more modalities in data. Of course, Ishan doesn't really need an introduction in this field of self-supervised learning. So with that, I want to welcome you.
Thanks. Okay. So thank you, everyone. Thank you for having me. Today, I'll be talking about why SSL skill matters in this era of basically multimodal learning. Right. So in general, for multimodal learning, there has been this like huge revolution where getting billions of pairs of images and text basically helps us learn representations that align images with text. And so CLIP basically being one of the most famous examples of this sort of learning. Now you're able to associate full-fledged text prompts with an image representation, and you can actually do lots of amazing things with it. So getting these aligned image text features allows us to do, for example, image text retrieval, open vocabulary classification, open vocabulary detection, segmentation, and also generative tasks where you can just take the CLIP model, try to invert its features, or try to use the alignment that it has learned for images and text, and then use that to do image generation. So given all of this, given the sort of progress on all the leaderboards, the scaling abilities of these models, the main question I've been asking myself is, does SSL even matter? Like, we've all been trying to push this for a while. We've all been trying to do this for a while. Does it really even matter? And this is more of an existential crisis question for me also at some point, because why are we pushing on these models if like all the sort of answer to getting good and better text image features is really just learning image text aligned features? And in general, there have been lots of answers or lots of answers that have refute this claim and show that SSL is actually doing really well. So earlier this year, we had a paper called Dino V2, where we showed that scaling SSL by just like standalone actually helps. And so compared to weakly supervised learning, like OpenClips type models on a bunch of different tasks like ImageNet, segmentation, depth estimation, and so on, these models actually do a pretty good job. But should this debate always be phrased as SSL versus weakly supervised learning? Should we always be like pitting these two things against each other and then trying to compare one model versus the other, and then basically given a particular timeline in basically research, we decide, oh, SSL is doing better, oh, SSL is not doing better anymore. And basically we can just keep on going through this particular cycle. So there should be a better way to phrase this thing. And I will want to argue that basically this SSL versus weakly supervised debate should actually be SSL and weakly supervised, and it should not be a debate. It should really be about figuring out how self-supervised learning can actually help weakly supervised learning. So in general, self-supervised learning methods, for example, standalone methods like MAE, really try to focus on learning these image reconstruction tasks, learn a better representation for this. And then I will call weakly supervised learning to be something which is using a noisy label supervision. So there was this work called Swag from Facebook that did this. By taking an image and then trying to predict a bunch of hashtags, scaling this up to billions of Instagram images, and then learning really useful representations. So in general, methods like MAE are really good for like downstream diverse tasks. They learn very sort of localized representations, very good for dense prediction tasks. And methods, of course, like CLIP or weakly supervised learning are really good for state-of-the-art like image classification tasks, zero-shot downstream abilities. And so they do seem to have very complementary sort of embeddings, complementary sort of properties in their embeddings. So in one of this work, which we'll present on Wednesday this for ICCV, we have a paper called the effectiveness of MAE pre-training for billion scale pre-training. And the idea is very, very simple. The idea is that we basically introduce a simple pre-training stage that uses self-supervised learning. And then we just follow it up by the standard pre-training stage, which is basically your standard weakly supervised learning. So in the pre-training stage, you try to do something like MAE, you learn these representations. And with that initialization, then you basically take all the image text data that you have in the world, and then you basically just try to pump that through your model and learn basically a model. And what we'll show is basically doing this pre-training stage is actually super, super useful. Not only for performance, but also for efficiency, also for scaling, and really that sort of matters a whole lot. All right, so the idea of pre-training is really simple. For the first stage, we use MAE. So we mask out basically 75% of the image, and then we feed forward the 25% unmasked tokens through the encoder, and then we try to reconstruct the 75% masked out stuff. And so this really makes this super flop efficient because the image encoder is only looking at 25% of the image tokens. In the second stage, once we have that MAE pre-trained model, we use that model and further train it on weakly supervised training. So we take images, we take their corresponding hashtags, so their text classification labels, and then we basically just have multi-target prediction. So we don't do contrastive learning in this one, but you can basically try to do clip-style training if you wanted to also. And just by using this like very simple mechanism, we get state-of-the-art models that do really well on image video tasks. So the pre-training model that we have is quite, the setup is quite simple. We have a data set of Instagram, which is 3 billion images. And we just resample them basically to make sure that these images have the long tail is sort of represented a little bit better. And so you get 5 billion images after resampling. And for the weekly supervised training step, we have a vocabulary of 28,000 hashtags. And for the model architecture, we'll use a standard vision transformer model, and we'll scale it up to about 6.5 billion parameters. So the first finding we have is that just in the pre-training stage, the MAE method scales with both data and model sizes. And so if you recall, the original MAE paper just shows this for just scaling a VIT model on ImageNet itself, does not really scale across the data axis. We find that it actually scales quite well across the data axis as well. So in the graphs over here, we're looking at ImageNet accuracy or iNaturalist classification accuracy. We're looking at two curves. So the dashed lines are showing MAE model being trained on ImageNet, and then the solid lines are looking at MAE models being trained on the Instagram dataset that I talked about. And so as you increase the model parameters going up to 2 billion, we actually notice that these models are, the performance of these models is actually improving, and there is actually a benefit of using this larger data. So we do see that this is actually doing quite well. So once we have this pre-training, we try to then basically use this for the pre-training stage. And so what we find is basically that pre-training actually matters at all sizes. So you can have a model of like basically a standard VIT model, or even scale that model up until like 6.5 billion parameters. The gain on through pre-training actually still holds. And this holds at billions of images, so like 3 billion or 5 billion images that we're using for training, and models that are actually really large. So this is not a diminishing return that we try to see, which has been one of the biggest issues with scaling up SSL models. So in general, in the blue line, we basically have the weekly supervised model that is being trained across different model sizes up to 6 billion. And then in green, we have the pre-training model. So you take MAE, you do the weekly supervised pre-training. And then we basically see that at every single point, it gives a big gain. In fact, the MA, sort of the pre-training model at 2 billion parameters performs better than basically the weekly supervised model at 6 billion parameters. So in general, that sort of also helps you reutilize these parameters much better. And the second thing we find is that it's actually a lot more efficient to do this. So on the left-hand side, we basically are trying to vary the number of pre-training epochs, right? So the blue curve is basically the standard weekly supervised training, which is not going to use any pre-training. And as all the different green curves are showing, just adding how like very little amounts of pre-training is actually going to help improve the model's performance. So you start with like this pre-training for just 0.1 epochs, and that automatically starts giving you a big performance boost for the smaller models. And in general, basically, as you're sort of increasing the amount of pre-training, that's the benefit that you're getting cross-training is actually improving. And on the right-hand side, we're also looking at the training flops versus the accuracy, because that's finally how you would want to measure something like efficiency. And in general, the pre-training method does seem to provide a significant improvement in efficiency. And so you get better accuracy as you're sort of training these models. This is all about efficiency, it's all about accuracy. Does it really matter for performance? And so when we looked at basically the pre-trained model across a bunch of different diverse tasks, so we looked at video recognition, image classification, object detection, segmentation, 5-shot, 0-shot, pick your favorite sort of evaluation method. And we basically have the MAE model, we have the standard weekly supervised model, and then basically this model with pre-training and pre-training. And so we can observe that the MAE model, of course, shines on dense prediction tasks. That's where its biggest strength is. The weekly supervised model typically shines on classification tasks, does not do as well on the dense prediction tasks. So typically an object detection that does not do as well. And doing this pre-training with the pre-training actually combines the strengths of both of these methods. And you actually see an improvement. So on majority of the tasks, it actually surpasses either of these models, while basically using a model of the same capacity and using the same exact training data. And the other thing result we have is basically that when we take this model, we actually were able to set pretty nice state-of-the-art, basically best observed numbers for a bunch of these tasks. So for iNaturalist fine-tuning, we basically have the best number now, which is 91.3 for accuracy. the one-shot ImageNet number, where you basically just take one example per 1,000 classes and then just try to figure out what the model's performance should be, we get like 62.1%. And then in general, for out-of-domain evaluation on ObjectNet, we actually have 75.8% accuracy, which is the best reported one. All right, so in some way, if you were looking at just image text as your source of supervision, there is now some evidence that you can actually use SSL to benefit those models. So you don't really have to view them as competing techniques. You can actually view them as complementary techniques. And this pre-training is a very simple way of combining both of them. That still does not answer more questions, right? So what if you do not care about language? There are lots of people, for example, Alyosha Efros, who starts complaining about using language for lots of things. And well, this is true, right? Because in general, multimodal is not equal to bimodal. So when we say image and text and we immediately go from single modality to multimodality, we basically just sort of ignore the fact that there are a lot more modalities. We just start talking about two single things over here. And as you look at different types of modalities, basically beyond image and text, you start noticing a big problem. In general, getting aligned data for different modalities is really hard. So for image and text, you can basically get lots of data from the internet where you have images with their corresponding text. This part just starts getting harder for modalities like depth. For depth, for example, just getting data itself is hard at scale, at the same exact scale as images. And then to ask for aligned data where you actually have well-formed text descriptions with the depth maps is going to be harder and harder. And then for other modalities, thermal, motion, audio, this also starts getting harder and harder. So in general, you have lots of aligned data for image and text and not as much aligned data for the other modalities. And so how do you sort of try to use all of these different modalities and still try to get aligned feature representations? So in last year's CVPR, we had one solution to it, which we called Omnivore, where the idea was that you take a single model and you basically feed it different types of modalities. So in this case, image, video, and single view 3D. And you feed it from 3 completely unrelated data sets. So these data sets are not aligned. So you basically like feed it ImageNet, you feed it something like kinetics, you feed it something like Sun RGPD, and then you train this model. And because it is using shared parameters for basically modeling all of these 3 different modalities, we observed something pretty amazing. In general, cross-modal alignment seems to just naturally fall out of this model without actually training it for this. So what I'll now show you is in the Omnivore embedding space, if we try to do something like nearest neighbor, what does the model think are related concepts in this feature space? So we have an image, so the RGB version of it. And then we look at its nearest neighbors by feeding through depth maps through the Omnivore model. And we find that it is actually looking at the same exact concept when it's trying to do nearest neighbor retrieval. The same thing holds for single view 3D when you actually are looking at RGBD. And the same thing also holds for video. So it's basically able to get videos of this exact thing. And note again that the model was not trained to do any of this. It's just falling out of it because it's using shared parameters. And so just by looking at these modalities, we're getting different things, right? So the image is telling you about the texture of the pineapple. The depth map is giving you some sense of the shape of the pineapple. The video is showing you that you can actually cut and eat pineapples probably. And this sort of holds for a bunch of different things. So you can do this, basically, you can stare at these samples. And in general, this does seem to fall out for a lot of different images. So what this basically shows is that in general, images seem to be a pretty universal language, right? So wherever I talked about the fact that it's hard for us to get aligned data, I was really looking at image text or audio text or IMU text or depth text type of examples. But we should also look at the fact that whenever we're capturing a bunch of these things, naturally our sensors are also capturing a corresponding image modality. So depth sensors typically are equipped with an RGB sensor. So you will get RGBD, you get RGB for free whenever you capture depth for most of the times. The same holds for thermal sensors. They actually have the infrared cameras do capture visible spectrum as well. For motion sensors, it's the same thing. The same thing holds for audio. Most videos actually have audio. So to do video learning without audio, we basically just throw away signal to then pretend that we just have video. So we actually do have audio as well. And so all of this stuff is basically naturally coherent, right? We don't have to go out of our way to get this. So it's really going to be self-supervised if we try to use this signal in some way. And so earlier this year, we had a paper called ImageBind, where we showed that you can actually use all of these, you can use the image modality to align different types of modalities And once again, this is complementary to using something like a weakly supervised method. So it has nothing, and you can actually leverage weakly supervised learning and just enhance it by using image bind. So the key idea is quite simple. We have our images, which basically naturally co-occur with all different modalities. And for each modality, we will try to just align it to its corresponding image modalities representation. So for example, we have depth co-occurring with images. So wherever we have that, we just take a train a depth encoder and we try to align it to its corresponding image encoder's representation. The same thing holds for thermal, the same thing holds for IMU. And so everything basically aligns itself to the image representation for which it's naturally co-occurring. And what we observe is a pretty remarkable phenomenon. It's that we get transitive alignment out of this. So after training, we find that because we've been aligning everything to images, we're actually able to observe that the modalities themselves are aligned. So basically depth and text, we did not train we don't have a single training example of depth and text maps co-occurring. But after aligning everything to images, we can actually now take the depth embeddings of the model, the text embeddings of the text model, and we actually can view sort of good correspondence between them automatically. And this behavior basically seems to emerge for all the different modalities that we have studied in this case. So the training setup is that we have 6 modalities: image, video, text, audio, depth, IMU, and thermal. And we'll only train with image paired data. So we will not use any other data. So it will be either image text, image audio, image depth, image IMU, image and thermal. And for each modality, we'll have a separate encoder. Like I was mentioning, this is basically complementary to something like weakly supervised learning. So you can initialize your image and text encoders with something like a clip model. So where you just have an image and text aligned embedding, and now you just freeze this particular image encoder, and you will try to align your different depth encoder, your IMU encoder, your thermal encoder to the image encoder. And so at test time, we try to just measure first the emergent alignment. So by training on these pairs of image, X, where X is a particular modality, we will now try to test what happens if that modality X is being aligned to text or not. So whether that alignment is good enough or not. And so to do this, we basically have this task of emergent zero-shot classification, where you're trying to just do the standard zero-shot classification like clip. So you come up with a bunch of different prompts. You try to find a prompt that basically has the maximum similarity with your particular embedding, and then you just pick that class, and then you can measure a classification accuracy or a retrieval accuracy. And so for all of these different modalities, for the image and video tasks, basically we are using a clip encoder. So of course, we sort of maintain the performance of the clip encoder for these tasks. But for these newer modalities, depth, audio, thermal, and IMU, where we did not have any text supervision, we find that image bind is actually able to give a strong improvement in performance over something like a text-paired baseline in lots of cases. And this is without the model observing a single pair of text when training. In some cases, it actually comes quite close or even surpasses a model that was trained using text supervision. And that really just has to do with the fact that you're leveraging a lot of supervision when you're using image text encoders, and you're just sort of adding these other modalities on top of it. So that really gives a strong advantage. Now, beyond numerical sort of comparisons, image bind actually has a variety of different applications. So the first one is basically for upgrading your existing models. So in general, you have your favorite model. Unfortunately, it only understands text, and you want to feed it a different modality. And so with image bind, we can basically upgrade this model without any retraining, because we have aligned embedding spaces, and we can feed it a different embedding. So we can feed it a new modality such as audio, or we can feed a new modality such as IMU. And you do not have to change your model at all. The same exact model just works with a new modality without having to do any extra effort. And so, for example, if you had a text-to-image generation system, so this text-to-image generation system just takes text prompts and generates images. Now you can actually just change it to understand audio prompts. So you just feed it an audio of a dog barking, and then the model basically, because it's using aligned embeddings, can generate pictures of dogs. Or the same thing happens for something like fire, engines, rain, and you can basically just feed it any type of audio. You can do the same thing for a different modality, maybe even feed it depth maps, and all of this does not require any training. The other property is that these aligned embeddings can actually be added. So you can take an embedding of something, of an image, so in this case, a bird, And you can add an embedding from an audio, for example, the sound of waves. And because these embeddings align in the same space, you can add them and you can actually compose their meaning in some way. And so when you try to do retrieval now, you'll actually get images of birds with the sound of waves. So presumably in some type of water setting. And so you do actually see birds being retrieved with some type of water behind them. The same thing exists for if you try to do this something for this clock. You have a clock and the sound of church bells. So the model does sort of put them together. It retrieves clocks basically on churches or on buildings. And then when you have fruits and birds, it basically retrieves birds eating fruit. So it's able to sort of combine both of these things together. So you can compose different modalities, and that really works out well. And so with this, thank you for listening to me. Presented these two things. I'll also advertise a third poster we have on unsupervised object discovery called MOST, which will be on Friday. Thank you.
Thanks. Any questions, please raise your hand.
So my question is about the training of 0.1 for how anything more about that?
Oh, for the MA pre-training stuff? Yes. So essentially the point is that if you're trying to just like do this pre-training, you can decide to do it for a certain number of iterations. And so what we were trying to study is how many iterations does it suffice to basically, have a reasonable pre-trained model. And so what we observed basically is, okay. Yeah. What we observed is that you can sort of continue pre-training the model for a while and like up till one epoch, and that does give you benefit. So in general, sort of improving, sort of having a longer pre-training phase does seem to help performance overall. Although you can, like, what this is also showing is that with a small amount of pre-training, you actually do get a large benefit already. So the returns are diminishing, right? Because with the 0.1 pre-training, you're already seeing a large delta compared to the blue line. And then for every sort of marginal 0.1 to 0.2, you're sort of doubling the number of iterations, but the improvement is sort of getting smaller and smaller.
Hello, thank you for your presentation. And also, I would like to congratulate you on the fact that you never did a mistake on asking pre-training, although it's a bit tricky. Yeah, so my question is on this pre-training, stage pre-training of models. So you did this in a sequential manner, right? So you first training master and public, and then train this provider. So how about you combine these two stages? Like does it work like multitasking? Okay.
Right. So the reason we went for the sequential approach is just its pure simplicity. When you would have the multitasking, I don't think we trained it absolutely at scale, but just like balancing the losses, figuring out like how to batch it, how many gradient steps to get from one task versus the other seemed a lot more complicated. And this setup was just simple, and you were just surprised that it was working really well. So we just like decided to push it all the way and see. Maybe multitask learning does work out, but you would have to figure out how to balance the losses and maybe like figure out how to alternate the batches, or are you getting the same signal in the same image, same batch? It does have a lot more design decisions to it than this setup.
Yeah, that's true. My second question is, before the break, we saw that the accounting models, we see that certain skills are not and certain features are required. So in your final plot, you show that after the second stage of the training, performance is preserved. So do you think this is because these also are complementary, or there is some more effect in the fact that the second pre-training stage continuing with the supervisor back on some of the time?
Right, so you do notice a little bit of regression on the dense prediction task, right? So if you look at the COCO AP box number, the MA model is slightly better, right? So the pink thing is like exceeding the green in this case. So there is a very slight regression, but I think in general, the reason is that for most of these tasks that we look at, weekly supervised training does do a really good job. And so that sort of doesn't go away if you fine tune it for longer with weekly supervised training. And I would view this more as like the pre-training stage gives you a very good initialization point, which helps you learn very fast. And so that's why you actually see like faster convergence, you see better performance for the same amount of like training iterations.
Thank you so much. Right. Let's move to the different side now.
Thanks for that. Could you comment on the image point where your binary between two images, right? So for some modalities like motion, we have very less data, let's say motion capture or something, compared to other modalities, right? How do you balance them in that sense that you balance the contrasting loss or like how do you in general approach that?
Right. So this is a great question. I think so the design decision we made was to actually have different encoders for each modality, so we could adjust the capacity according to the amount of data we had. So for something like IMU, we actually did not have a huge amount of data. So the encoder that we use is actually smaller. And so you're not really training all of them at once, right? In some way, you can think of it as like launching 6 or 7 different parallel jobs, which have nothing to do with each other. Because the image encoder is a fixed target for the IMU encoder, and that's it. So when you're training the IMU encoder or the motion encoder, it does not even know that there is basically a text encoder or there is a video encoder or there is a depth encoder, right? It's being trained completely independently. So you don't need to worry about balancing the losses. All you need to do is basically find the best encoder that works out for your IMU, and you can adjust the capacity, you can basically adjust the parameterization, you can adjust the batch size for the contrastive loss, even maybe if you want the temperature for the contrastive loss, you could actually adjust all of it independently of the other modalities.
I think we have time for one more questions.
Hi, thank you, Professor. So when you do the pre-training, you actually introduce two new things, different training strategy and new data. What would be the relative benefits between the two?
Right, so we did verify that. So the previous work that I talked about called SWAG, we did verify that the data that we're using is basically comparable to the work that we had called SWAG. So the data is roughly the same. So in the sense that for all the model comparisons, like in this entire thing, the weekly supervised baseline, the MAE baseline, and the MAE plus weekly supervised baseline, all of them are using the same exact data. So we're controlling for the effect of data when we're trying to like come up with these like comparisons. The only reason for going to the large data is to show that it's not a saturating effect. So for example, if I were to do this with 1,000 images, then basically we know that with 1,000 images, the weekly supervised baseline is not strong enough, right? So the question is really about, does SSL matter at scale? And so if you were to push this for like your best model that exists today, which is basically going to be a multi-billion parameter model trained on multi-billions of images, would SSL still matter? And so I think that's the question we were trying to answer.
Last question. Over there.
Hi. So in the image kind of paper, so suppose in your pre-training, we never had audio, right? And we had all these other modalities, and now we give the image of a car in a rebrand, the hashtag, and then the audio of waves. Would that still align at inference time? Because because the audio is never in the pre-training setup, with the audio modality is never there. But now suppose we just add an encoder and somehow align the encoder and immediately there's that data space. How maybe did you try that, or maybe would that go crazy, or would it still, because now it needs to be aligned with other modalities? You get the
Not really, no, sorry.
Right. So suppose like you did during the training, you never had audio modality. And now you give an image and then you kind of try align just an encoder with this audio, with that latent space. And you do the addition of modalities between the image of the duck and the sound of the waves coming in. Would the duck be the C region or something like that, the generation? So it's like you're adding new modality in the future, you know.
I see. So is your question that basically when you're training the audio encoder, suppose you had only 10 examples rather than the audio data set that we used? We did not experiment with the amount of data, but like I mentioned in the previous case, the encoders can be of very, very different capacities. So if you have an encoder that is actually very small and you adjust it out to the number of samples that you're looking at, it may work.
Right, thanks.
All right, let's change again for.
For the next talk, we have Sayak. Sayak is a research engineer at Hugging Face. He works on training and babysitting diffusion models on Hugging Face.
I'm just trying to do the.
You don't need to do screen recording. I think if you go there and press on share screen and press share again. System preferences. And now you need to turn this on for Zoom. And quickly reopen. Great. All right.
Good to go. Cool. Sorry about the technical difficulties. Yeah. So as that was my one-liner introduction, I work at Hugging Face as a research engineer. I work on training and babysitting diffusion models. I thought of putting the babysitting word also in there because that's very important. So yeah, let's get started. There were lots of talks around the classic pre-training era, like self-supervised learning, semi-supervised learning, noisy supervised learning, and so on. But let's get to the text to image part a bit, and let's see how we can sort of adapt this big text to image diffusion models for a bit. So, and as a disclaimer, this talk is not going to be an exhaustive overview of all the possible methods. So I just wanted to get that big elephant out of the door right away. And yeah, let's enter the era of text to image diffusion models. I'm sure we all are kind of familiar with it at this point in time. So we have Imagine, we have DALI 2, and then we have Stable Diffusion XL. All these are pretty remarkable text to image diffusion models, giving us like hyper photorealistic results and so on. And let's kind of also revisit how diffusion models work in a jiffy. So the way I like to understand diffusion models is like asking the following question: what happens when you try to refine a noise vector to become a realistic image? And you can catch the infographic. Like we are trying to slowly and gradually introduce noise to an image, and then we are trying to basically denoise it in an iterative manner. And when you try to condition this denoising process with text, you get something like this. And I'm sure we all can agree that in reality, the spar monsters cannot really exist. So yeah. And it's also crazy to think about how these big text to image diffusion models sort of learn to disentangle the concept decomposition, and how they sort of learn to compose and combine different concepts into each other to generate and arrive at a particular image. So on the left hand side, you can see on images how models like Stable Diffusion, how they learn to sort of decompose images. And on the right hand side, you can see how a single image can be sort of decomposed into a series of different, albeit a bit potentially contradictory, but they are decomposed into multiple concepts. But we will try to also disentangle some of these limitations, and we will also discuss some of the solutions that can be used in order to mitigate some of the limitations. But for this talk, we will focus on latent space diffusion models. Just to give you a brief idea, DALI 2 it's not a latent space diffusion model; it's a pixel space diffusion model. But for this talk, we will focus on latent space diffusion models. But some of the ideas can equally be applied to pixel space diffusion models as well. And more specifically, we will target the stable diffusion family because open access and open source focus. So yeah. And let's come to part one. And I'll throughout my talk, I'll cover both training only and inference time techniques. So it will be a good mixture. So yeah. But most of the techniques that will require some sort of training, they are very cheap to do. So don't worry about it if you do not have access to clusters. So first problem is subject-driven generation for personalization. Even though this text-to-image diffusion models are kind of really amazing at generating hyper photorealistic images, but when it comes down to generating really subject-driven stuff, they kind of fail. Like their fidelity is not on par. We are not able to sort of generate particular subjects in interesting renditions and so on. Even if you try the image-to-image translation systems with any text-to-image diffusion model, they kind of fail. So we are basically interested in rendering concepts or subjects that are kind of new to the models in interesting contexts, and thereby induce some sort of personalization. So it's actually possible. So the problem basically comes down to this: how do we introduce new concepts to a text-to-image diffusion model? And surprisingly, this work from Google called Dreambooth, it works pretty well even to this day. It was introduced in 2022, and hyper realistically in all the applied subjects that I have seen, Dreambooth still works. So the idea is to kind of cheaply fine-tune your text-to-image diffusion model on just a couple of samples, and during the inference time, you basically add or append the new identifier in your prompt, and you basically reap the benefit out of your cheap fine-tuning process and be able to generate these cute characters in interesting renditions. So without the loss of generality, let's be a bit more specific about how this text-to-image diffusion models are trained. So we will assume X is our original image, then we sample some noise from a Gaussian distribution, then we also sample some time steps from a uniform distribution, then we have some sample quality controlling factors, then you have your conditioning vector, which can basically be anything, but again, the text embeddings are usually the conditions that are used for training these models, and then you have your diffusion model that is to be learned. So during training, we basically append the conditioning vector to the sampling process, and then we basically learn the text conditioned diffusion model, which is basically and during inference, we basically we try to sort of refine a noise drawn from Gaussian, conditioned on your text prompts, conditioned on the text embeddings, and then voila, you have your images generated. Now, what the Dreambooth authors do is, it's pretty interesting. They introduce a prior preservation loss so that the model does not lead to catastrophic forgetting, because you are basically showing the model three or five images of the new concept that you are trying to make the model learn from. But during the process, you also wouldn't want the model to forget about the earlier stuff it had learned about that particular subject. Like if you wanted to introduce a new concept of dog, you wouldn't want the model to forget about what it had already learned about the dogs it had seen during its pre-training process. So the idea is basically to sort of sample a couple of images from the pre-trained text-to-image diffusion system, and during the fine-tuning process, you also sort of augment your data set of 3-5 images along with this prior preserving images, so that the model does not incur catastrophic forgetting. So that's basically it. And one framework, and Dreambooth is very generic of a framework, and we will see why in the results. So one framework, multiple use cases. So let's first discuss general subject-driven generation. So during the fine-tuning stage, it was basically shown images like this. And on the right-hand side, we were able to sort of render the same subject in front of an Eiffel Tower. So I had to be a bit more, conventional. I had to take this image as an example because we are in Paris and Eiffel Tower, whatnot. So yeah, my point is, it was not shown during the training process, but somehow, by the virtue of the dream booth fine-tuning process, it was able to sort of learn the concept of this particular term relatively quickly, like 200 steps of fine-tuning, and then we have it. But the incorporation of the priority reservation loss so that the model didn't do any catastrophic forgetting, that was kind of very important. And then we can do art rendition, like on the left hand side, we can see our training samples, just 3 or 5 training samples, and then we can render that new dog into interesting contexts. And then we also can do property modification, which is kind of cool, like image editing and stuff like that. So one framework, multiple use cases. Now, the community has been pretty crazy with Dream Booth. They have kind of pushed all the extremes of Dream Booth. So I highly welcome you to check this demo application out. We are also presenting a Diffusion's demo on Wednesday. But if you want to, feel free to check this demo out to see how far you can really push the Dream Booth results. Now, here are some further reads. Like if you wanted to achieve zero-shot subjective event generation, believe Diffusion from Salesforce, it's a pretty interesting read. And I think before Dream Booth, there was this paper from CMU on custom diffusion. It's also pretty interesting. It lets you do multi-subject fine-tuning with stable diffusion. And then there's a pivotal tuning as well, which basically combines Dream Booth and textual inversion. I know pivotal tuning is a bit different in the GANs world, but in the diffusion world, it's basically a combination of Dream Booth and textual inversion. Now let's get down to the other limitation that I wanted to discuss, and I'll also present some solutions. So, of course, text-to-image diffusion models are again very great, but the only conditioning factor that we can truly control is just the text prompts, right? But the question here is, what if we wanted to also condition the generation process on a pose image along with some language supervision? So what if we wanted to do this, let's say? We wanted to generate our subject to adhere to not only a text prompt but also a pose image. So the regular text-to-image diffusion models won't be able to do that. By the virtue of pre-training, they won't be able to do that. So we need something special here. So let me introduce the concept of control net, which is basically an auxiliary network, kind of initialized from some of the blocks from the unit that's used in the text-to-image diffusion system of stable diffusion, and then it's basically trained along the way on image space conditioning, and more specifically, the training formulation that we saw a couple slides ago, we also throw in the image space latent conditioning that's computed from your control net. And control net, again, it's initialized from some of the very specific blocks of the unit that comes for free from your text-to-image diffusion system. And then what we basically do is we feed the unit with the same inputs, but we also feed the control net with an additional conditioning image such as the pose image, and then to the output of the unit we basically add the output of the control net, so that it's not only just conditioned on the text prompt but also it's conditioned on the embeddings computed from the control net. And control net, it's basically learned, but again the training process is cheap. And again, the results are pretty powerful. Like you can train a control net on sketch conditionings, normal maps, depth maps, scanning edge filters, sketches, segmentation maps, and so on. So I think this truly kind of gives you the flexibility to kind of control this text-to-image diffusion models on additional multiple modalities. There were some points made by Ishan on using multiple modalities, like going beyond the text modality, and I think control net exposes a very powerful yet flexible framework. And shall I say controls, because it's absolutely possible to combine this multiple control nets. Like let's say you want to have one image condition on canny maps, and then you also wanted to condition the generation process on poses with this prompt, a giant standing in a fantasy landscape based quality. And it's possible to combine multiple conditions along with your natural language supervision. So I truly feel that control nets kind of expose a very powerful framework here. And it's of course possible to go beyond just two image control conditionings. You can combine multiple ones like 5, 6, and so on. But this is truly powerful. Right, here's some other interesting reads like T2I adapters. They are very similar to control nets, but they are much cheaper and easier to train, and memory wise they are much smaller as well. And then there's IP adapters, again very smaller and faster. And then there's instruct pix to pix, which kind of deviates from this line of work, but gives you a very solid and powerful framework to actually edit your images using natural language supervision. So consider instruct pix to pix as some sort of an instruction fine-tuning way, but for text-image diffusion models. Right, let's come down to the third limitation and discuss some solutions. And this will be an inference time solution. At this point in time, we were talking about training and fine-tuning these models, but the solution proposed for the third limitation would be inference time only. So yeah. So catastrophic neglect and incorrect attribute binding. So on the left-hand side, we have two images basically, where we can see the stability. So it's stable diffusion v1.5. So it was not able to actually generate one or more subjects in the generation process. It basically neglects that object. So it's this phenomenon is, again, the results are not cherry picked, and this phenomenon is known as catastrophic neglect. And on the right hand side, you can see that it fails to properly bind attributes to objects, which is kind of problematic, right? But why? So I'm going to steal a couple of slides from Gila Schaffer, who is the first author of Add in the Next Slide. So let's review the DDPM process a bit. So given an input text prompt, we want the DDPM model to gradually denoise a pure noise latent into an output image. And then for systems like stable diffusion, which are conditioned on natural language prompts, we have image latents, and again we are talking about latent-space diffusion models, not pixel-space diffusion models. So we have image latents, and then we have frozen text embeddings, and then we have the cross attention maps. And if we index into this attention map, it basically denotes it quantifies the presence of the token in patch I. And a bit more visually, if we consider this prompt, a lion with a crown, we can see that some of the tokens are actually getting neglected. If we probe the cross-attention maps, there's no like strong activation of this subject tokens in the first place. So this is the problem. Crown gets very low attention values for all these patches, and inherently in this systems, in this text-to-image diffusion systems, there's no inherent incentive for these models to actually, supercharge the attention values for all the patches. Now, how can we basically fix this? But before we go ahead and fix this, the idea for the fix would be to encourage the model to better consider the semantic information passed on from the natural language text prompt, and we would also want to ensure that all the tokens are attended to by some image patch meaningfully. But inherently, there's no mechanism to ensure we are doing all of these things. So yeah, the simple intuition here is a generated subject should have an image patch that significantly attends to the subject token in the first place. And the idea kind of further elaborates to strengthen the activation map of the most neglected subject token. So we formulate that into a mini training problem, a mini optimization problem, which can be done using stochastic gradient descent on the fly when you are basically generating your image, and it does not also introduce too much generation latency at the same time. So it's basically formulated as a mini training problem, but the idea is to maximize the activation maps of the most neglected subject token. And yeah, this is how it's sort of put together. And we want to also ensure that all the subject tokens are attended to and excited, and none of the subject tokens are kind of neglected. And the results are kind of pretty amazing. This method basically works. We can see there's no, again, the results are not cherry picked, and we can see there's no catastrophic neglect. And stable diffusion also is able to kind of bind all the proper attributes to the underlying objects very easily. So here are some notable mentions that I couldn't include in my slides. If you wanted to control subtle semantic attributes, and if you wanted to sort of do that in a training-free manner, semantic guidance, it's a pretty cool work. And of course, you can do a lot with just your prompts. If you want to sort of write very elaborate prompts, then rich diffusion, the work on rich diffusion, it's also pretty cool. It introduces the idea of controlling the generation quality by introducing rich text prompts, and then it's also possible to improve the discriminative performance, the ImageNet, the classic seminal ImageNet performance, by using synthetic data sampled from diffusion systems. And yeah, that's about it. If you wanted to get access to the slides, feel free to scan it. And I think we have we have time for questions and answers.
Great, thank you for the talk. By the way, when you go back, if you come to the front, there's at least 10 to 20 seats spread around. So now is the time to learn to start. So, all right, who has the first question? Yes.
Hi, this is Bruno. I have a question about Dreamboot. So you were saying that it's a way of introducing new concepts to the network, but most of the time it's about subjects. And is there some experience with a more general concept, like some kind of object class in the code and not just a subject?
Oh, so you want to impose some generic object idea into the model rather than a very specific subject. Is that what you're asking about?
Yes.
Oh yeah, blip diffusion. You should check out blip diffusion. It's pretty cool. So it introduces a generic image encoder, which you can then again go ahead and fine tune on just a couple of 10, 15 samples sampled from your object class that you want the model to learn, and it basically outperforms Dreamboot on that scenario.
Thank you. One more question.
Go ahead.
If all the adaptation methods, all that, and so on, do you think they will remain significant after models, like the next version of DALI comes out, that might be fixed?
I think methods like Dreamboot will still find its value because it's very cheap and it just works in practice. And you can also pipe in parameter efficient fine tuning techniques like LoRa and QLoRa with Dreamboot, and they just work great. And it's also possible to do multi-subject fine tuning with Dreamboot. It's possible to extend Dreamboot to do multi-subject fine tuning. So I think there will still be some value.
Yeah. Next question.
I think that's
all right.
Yes, I have a very vague question, but in your example of the crown and the lion, the activation function of the crown is not really strong, and the crown is not actually on the result. But does it appear because I mean, if you are trying with another animal, is it likely to don't work again, like with the lion, or is it just association of these two words that is not working?
Yeah, so the repercussions are kind of uncertain here. So in one of the works I presented, Conceptor, they show that there's no inherent mechanism for the model to sort of decompose concepts in a way you would expect. For example, if I were to go back to this slide, you would see like sweet pepper is decomposed into very disparate things, right? There's no need for us to have fingers or something like that. So the repercussions of doing what you are proposing, it's kind of very uncertain at this point in time. So inference only mechanisms that ensure that kind of does it in an explicit manner, as explicit as Attarian said, that just works. They kind of enforce that association part inherently by sort of formulating that as a mini optimization problem. But otherwise, I have not seen anything that does it in a meaningful and expected manner.
Next question. Yes.
You talked about control net, and you mentioned about the Visual Adapter. Control net is more like Visual Adapter is more efficient, right?
Yeah.
So we should also know the control net. Why don't you?
There's always a trade-off, I must say. For in our experiments, what we have found out is for more complex image space conditioning, control nets tend to work better, probably because their architecture is a bit more complicated, and the more number of parameters kind of come to the advantage. But for most part, T2I adapters are great. But this observation is especially true for stable diffusion XL, but if you again come down to the stable diffusion world, control net results are far superior than T2I adapters.
More heavier.
Yeah, you could say that. Yeah, you could say that. You can even go ahead and do LoRa on control nets. But T2I adapters, if you sort of step them up in the stable diffusion XL regime, they just work better.
Last question. All right, if not, then let's thank Sayak one more time.
Cool, thank you.
No, it's okay. That's the rest is gonna happen. It's okay. It's still the investment. So okay, it's not likely sure or not sure or not.
Okay, so yeah. Hello everyone. So let me do a brief intro of Carl. Our next speaker, Carl Vondrick. Carl is an associate professor in Columbia University. He has a wide range of interesting vision perception, also on large language models, audio, and robotics. The title of the talk is Visual Intelligence via Code Synthesis and Execution. The stage is yours.
Thanks. Okay, so we all know there's these great chatbots now, and they're really good, right? They know the boys are eating muffin. They know where the muffins are, right? But these chatbots, these huge models, they still make these errors. They still have these funny errors, right? They can't count. They're not very good at that. Yeah, the joke here is that what's worse is that they interject their own opinions onto their matters too. Okay, so most work that you see, I mean, a large majority of the work is all end-to-end neural nets, right? These black boxes that are mapping images and questions to some sort of answer. And it's been a great run, but they have a lot of limitations that we often talk about as a field. Their math and logic abilities are quite poor, right? There's no explainability, like we are black boxes. We don't know what's happening inside of them. The compositionality, I don't know, it's not clear they have compositionality. We don't know what's going on inside of them, and it won't generalize to new situations all the time. There's bias, right? We got to audit, understand the bias, and correct the bias, and there's hallucination, and it just makes up facts. So we've been sorry. Oh, sorry. So I guess both mics. Okay.
You're too tall.
I need two mics. Okay, so we've been working on this approach that I'm really excited about, which is trying to do visual question answering with these large models by synthesizing code or synthesizing programs that you can then run to solve the problem. So here the question is, how many muffins can each kid have for it to be fair? And it creates this Python program that you can directly run and interpret each intermediate step. It's going to find the muffins first, that's a neural network operation, and then count them. That's not a neural network operation, that's symbolic, right? Counting is easy for computers to be doing, you don't need to learn it. And then it here, in this case, it's encoding that fairness means an even split, and it means just the divide those two, right? We don't have to learn that. Division is easy, it's solved problem in computers. We don't need to teach our neural nets to be doing that. I think what's really interesting about this is that, machine learning fairness is a really big topic. Here we can actually audit and understand what does it think fair means in this case, and it thinks fair means it means an even split. That's not always the right thing, right? If one kid is more hungry than the other kid, probably you don't want an even split. So I want to use the P word here, which I think this is an emerging paradigm that's going to become much more popular, which is to synthesize and execute a program to solve a variety of different computer vision tasks. And we're not the first to be looking at this. In fact, this has a really long history in the field, almost a decade at least, which is going back to neural module networks from 2015, which they were one of the first folks to propose this idea of breaking this down into a program generator and then an execution engine. You want to separate the reasoning from the execution. And at the time in 2015, they built the domain specific approach to solve this. It wasn't Python, it was a domain specific language, but it was really hard to get working. There's no supervision for it. So how do you train all this? They had to rely on reinforcement learning to do it. But that's always a disaster when you have to use reinforcement learning. So the main kind of innovation here is that we can basically replace this program generator with a code language model, these big models. And just by prompting it, you get these amazing programs that you can use. We think of this as something like a system 2 for computer vision. So for folks who are not familiar, system 1, system 2 is this idea from Daniel Kahneman. He has a whole book on the topic, Thinking Fast and Slow, which is about how there's two different systems of thinking inside of your mind. System 1 is spontaneous thinking, like pattern recognition, very fast, it's cheap, you just do it all the time. Most of your life, you're in system 1, right? At the chair, it just recognizes the pattern. While system 2 is more methodical, where you have to think through things, you stop and think, right? Playing chess, this kind of engages system 2 for you. So as a machine learning and computer vision field, I think we have basically built really good methods for system 1 right now, and we don't really have the system 2, right? This is something that is missing. And I think what this code generation does is actually provide a potential solution here. I think it's a really nice way to have system 2 as well as the integration between the two. And this is, I think, the beginning of this neural symbolic revolution. I really think 2023 is going to be the year of the symbols. And there's been just kind of it's quite bold. There's much more work that actually come out just in the last few months about this, just about combining neural network and symbolic approaches. And what's wild about this is I actually, like last year, I didn't even consider myself symbolic approach. I thought I was a symbolic person. I didn't think that would ever work, but I believe now, and I think it's going to work. So the way this works, this system works, is we basically provide it with a variety of these different tools that it can use. And some of these tools are system 1 tools, like pattern recognition. So it has like a function for find or computing depth. But we also give it access to basically all what Python has. So it can sort, do if statements, it can do loops, it can do math, right? It can do anything that Python can do that, anything in the Python library is able to perform. It's unrestricted Python code. This is what is actually so exciting about this work for me. And we basically teach it what these tools are, right? Just through a prompt. So we say, well, there's this function called find that's going to take in some object name, and here's what you're going to get out of it. It's kind of like documentation that you provide to a software developer, you can provide here, and we code up these functions too, right? So these find we'll run some sort of glip or glip type model to do the detection. We give it tons of different tools like depth and same type of thing, and here's what it does. So the abilities of this system, I just think are really exciting, and I love playing with this. So here's an example where in this image you have to. The task is to find the drink with 0 alcohol. And this is, I think, actually a pretty complex question because you got to combine different skills, right? You got to find all of the drinks, recognize the drinks, but then you also have to have some sort of knowledge about which drinks have alcohol in or not. So if you just take a kind of a standard, big neural net to solve this problem, it has to encode all of that knowledge inside the weights of a single neural net. It's really hard to do that, right? Recognition and knowledge about things. With this code generation based approach, it basically can break this down into these atomic steps that can then be compositionally combined to answer this. So it builds this program in this case. This is customized just from that query to basically first find all the drinks and loop through them to look up the name, to figure out the name of each drink, and then ask another language model, does that drink have alcohol or not? Right? And it can loop through all these until it eventually finds a Dr. Pepper, which says no, it's not alcoholic. Return the answer. So it's interpretable to some degree at each step. We often talk about this. I think over the last few years, we've been talking a lot about this, about the spatial reasoning abilities of these systems are actually quite poor. Like clip type models have a really hard time about, and diffusion as well, about left versus right. We saw this in the last talk as well. This is no problem for code generation based approaches. Like if you want to say find the second man from the left, this is easy. You can build a program, find everything that recognizes a man, sort it, right? Sorting is an operation that this has, and then just can look up the second index here. And you get consistency too. If I were to ask for the third man from the left, it would be almost the same program, but just looking up one more index. You get amazing ability to do logic and attribute binding too, right? Attribute binding is another issue we often talk about, and it's no issue. I don't think it's a problem because the code generation methods can do it. So if you have this tongue twister type of question, like, is the animal that is not gray a dog? It can build this program to reason about this. Finds all the animals, loops through them, figures out if that's gray, and then once it finds something that's not gray, it says, can figure out if this is a dog or not. So there's another thing we often talk about is like negation, right? How do you teach a concept of not gray? We know how to teach things that are gray. Like, should we be collecting data of things that are not gray and training it? No, right? This is making a pretty firm stance here, which is negation just is a symbolic operation that can just be encoded in the programs. If you can recognize gray, it instantly can recognize not gray, right? Just because of this program type of representation here. And the fact that it's able to shift its computation around and keep track of different objects means attribute binding is not going to be a problem, right? It's not going to be confused as to whether the cat or the dog is gray here. You get these, it's not really a vision example, but I love it so much. The math abilities are very cool. You ask a question like, with the depreciation rate of this car, what it's going to be worth in five years? So it builds this program. This is an emergent zero shot. We don't prompt things. There's no prompt somewhere to this type of question where it tries to figure out the name of the car, asks another language model what's an approximate depreciation rate, what's the approximate value for it, and then it actually writes out the log here. The line 11 here is too long to see in the full slide, but it writes out the log with everything to compute this to much more precision than you'd ever want. As to what the value is going to be in about five years. So you get this great math engine, right? This is stuff we don't, there's a lot of results about language models about how they can add small numbers, but they can't add large numbers, for example. Math is not going to be a problem, right? Through this neurosymbolic based approach with code generation. Something I'm really excited about this type of approach is you get adaptive computation for free. So if you have a video, like a long video, and your question is like, return the two kids that are furthest from the woman right before she hugs the girl, that requires an approach that actually can process this minute-long video. This is a long video, right? But we don't have feed-forward neural net approaches that can process long videos. Like you can basically put in a few seconds of video into most approaches. There's no way to have, we're not going to have full minutes or full hour videos being just processed in a single forward pass. So you get this efficiency with this adaptive, with this program generation, because it can shift its computation around depending on what part of the task you need to be solving. So here it builds this program to loop over all of the frames, doing a cheap operation first, looking for hugging, right? And the moment it finds that, it can then go, well, let's go backwards in time. It can shift its computation back in time to look at the frame right before to do more complex text processing. So I think this is going to be huge for video. I think this is how video is going to happen. You're not going to be backpropping through 2 hours of a Hollywood film. It's going to be something like this, where it's combining all these reasoning abilities. So there are tons of demos about LLMs and everything. We wanted to benchmark this, and a lot of the time we spent on this project was actually just benchmarking everything. And basically, the conclusion is you can get state-of-the-art zero-shot results from this. This is on referring expressions on 2 different data sets, where the bolded green at the bottom here. It's still worse than supervised approaches, right? So this is I'll talk a little about this and the limitations. This is, I think, the next milestone here is, can we actually overcome advanced supervised approaches? Visual common sense questioning tasks. Here's both two different results. And it's again state-of-the-art in zero shot. I put numbers on the right side because we're really proud of it, which is we were able to beat out Flamingo. Just 2 grad students could beat out Flamingo by more than a point. So the system does work in a zero-shot state, and in video you actually beat supervised approaches. So I think this is because of the efficiency that you get. I think another advantage, this is what interests me is, like, we've been talking about all these failures about machine learning neural network models for a long time. Like another failure I always talk about is consistency. You ask 2 questions and they're entangled, and the answer might contradict itself. With this program generation, you get a degree of consistency for free. This is how it happens. If you ask, like, what's the Euclidean distance between these 2 objects, it builds a program, and it can do the math in order to tell you whether it knows what Euclidean distance there is with squaring and everything. But if you change the question slightly and say Manhattan distance, it's going to be consistent, right? It's going to answer, it's build a very similar program, not changing it much, just to encode this consistency. One major limitation of this approach is about uncertainty. So this is making hard decisions at each step of the way, and so it's never propagating uncertainty throughout everything, right? All these classifiers, all these different tools are giving you confidence intervals, and we're throwing it away, right? So here's an example I really like, which is how old is this boy turning? Well, what do you guys think? How old is he turning? 4, it's easy, right? We count candles. That's kind of amazing, right? We know that. This also knows that. It knows that it can figure out its age by counting the candles. That's knowledge that it has. But it gets it wrong because it over-detects the candles. It thinks part of the cake is actually a candle. And so this is something that needs to be fixed, which is, I think that false detection is just slightly above the threshold that we set, which causes this error. So we need to develop approaches that actually can propagate uncertainty. It could be like that these are probabilistic programs that you generate instead, right? But it could be other types of approaches. In general, vision is the bottleneck. I think that's actually one of the takeaways here with these LLMs. Is I think that's to me one of the best things about this work is there's a lot of problems that we're solving that maybe don't need to be solved because the code solves it for us. And actually, the low-level, mid-level vision problems are the key questions in my opinion. Here's another example of this: how old are they turning? And we probably all say 25, right? We're able to read. We actually didn't code up OCR in this system, so it can't do that. So it gets it wrong. But also more generally here, the program generation is not conditioned on the image. The program is blind, right? So this is also I think it would be a really impactful step is actually to make the programs conditioned on the image instead of just the query here. It's very expensive to train those models. So I don't know if academics will do it. Maybe we can pull it out. So this whole system is available online. We tried to make it really easy to install. It's on GitHub, and we have a bunch more videos and demos and everything you can check out. It's a really fun system to play with. We've already had enough time to have all the bug reports come in to fix all the bugs. So I think it works quite well. This is work led by Vondrick and Sayak, 2 PhD students at Columbia here. I have about a half hour, right? Is my time? Yeah. Okay. So with questions. Okay, great. So I'm gonna talk about another aspect here, which is also about these big models, which is about spatial reasoning. How do you build spatial representations of things? So this is a funny video here. It's called What the Fluff Challenge on YouTube. You can go Google this and find a bunch of videos. It's basically this. It's a viral thing. But what it illustrates is an important point, which is, creatures like people, kids but dogs and crows and chickens and everything have object permanence. We have spatial representations. We know things still exist even when we can't see them. And when that expectation gets violated, we freak out, right? So here the dog freaking out about this. So this is a question where I think we've been thinking about a lot with these big models is how do we build these spatial representations? How do we create really 3D representations with everything? So there's been a lot of progress in 3D representations. Like there's one task, which is 3D reconstruction of a single image. Very hard problem because it's under constrained, right? But some of these methods work pretty well, right? Here's an example from occupancy networks, which is regressing that single image to this mesh. It turns out that if you slightly rotate the image a little bit, it kind of falls apart, right? And so these systems aren't very robust. We think this is basically an issue of data. So if you, this plot is actually to scale. I did the pi r squared and everything to make this right. So the area is correct in these two things. The big one is lying on 5B, the biggest academic, 2D data set that we have. When we kind of a year ago, that was the biggest 3D data set you could get 3D assets, right? Recently, there's a paper appearing at NeurIPS with Object Verse XL, which is a little bit larger, getting up to 10 million examples, but it's nothing in comparison to what you're able to get in 2D images. So I think that 3D is really held back by this, right? We just never even get as much data. It requires a human in the loop really to create these assets. Right? So we've been looking at a question. I don't think we've fully proven it yet, but we have good results to suggest this, which I'm going to talk about, which is, do these 3D representations emerge automatically in these large-scale diffusion models, right? These diffusion models we just saw in the last talk are from text conditioned, generally fantastic images. Everyone's seen all of this. And it's modeling the scene very well, right? It knows about reflections, right? It's seeing shadows, correct? Like, is there like a 3D representation inside of that model that's being learned just in 2D images? And if we could conclusively say yes, right, that would be really, really powerful because you could just train on all the 2D data that you have, or maybe video is really important. Video is probably very important for this too, but right, if you could train on all the available data and don't need to throw out 3D assets. So, the way these diffusion models work, and I think previous speakers have done a very good job of explaining it, is right, it's basically denoising, right? And so what we've been looking at is whether we can attach these camera controls to it. Can we add basically a control mechanism so we can rotate and translate the camera conditioned on an image? And the way we do this is basically you take this is one of the stable diffusion models trained on Lion 5B tons of data, and we're going to basically fine tune it with this new task with a much smaller data set to basically do view synthesis. So it's trained on the 5 billion examples, and with an object versus 5,000 times smaller data set, we're trying to teach it what it means to move the camera around. And what we found was this it's very simple, but we found this really cool system that could basically get state-of-the-art results at the time on view synthesis in order to change the camera view. It worked on kind of the typical data set that people work on in this problem, which is like, single objects, right? Knows how to move the camera with the shoes, right? Works on a little bit more complex objects too, like the drum set here, right? It can move it around. It's not quite right? It gets the circles in the wrong spot out there. But what's really cool, and the reason we called this 0, 1, 2, 3 is because the 0-shot results were just really cool. Like it worked on objects, or it worked on images that don't have a 3D object behind them, like art. So yeah, basically, Van Gogh and Pablo Picasso paintings, right? It could move the camera around, right? To predict what would it have looked like if from the behind of an object. And so we called it 0, 1, 2, 3 for 0-shot, 1 image, 2 3D object. And we also have a demo online. You can actually upload images on Hugging Face. Thanks for Hugging Face for donating GPUs used for this. So it's a demo, you can upload your own images and play around with it. It's super addicting. I've wasted a lot of time playing with it actually. So we in collaboration with UW, actually, we just released a newer model called 0123 XL. So it's a larger, trained on larger data. And this just has more, improves everything across the board. So it works on oil paintings, or it works on like cartoons, for example, like it can, rotate the camera for Pooh Bear. It works on line drawings, which I just find really cool, because this is not a 3D object, right? This is 2D, but we still can move it, and we can even maintain the style, right? This type of approach can even maintain the style, even though there's no 3D object. Okay, so this is obviously a very under-constrained problem from a single image, right? Because it's a generative model, though, underneath all this, you get really good uncertainty representation, and you can sample many different views. Like, I love this camera example on top. You don't know how big that lens is, right? So when you move the camera, there's an uncertainty. How big should you do that? If you sample from this multiple times, it just is going to generate cameras that are mostly consistent with the input there, but going to vary that camera length. Same thing for the lights on a car, right? There's uncertainty there. So this model I've been showing you is just doing view synthesis, though. Is there actually a way to like get just the 3D? Can we actually get a 3D model here? And so, one question is like, could we combine this with NERF? Is there a way to build like a NERF with this type of approach? NERF is typically hard because in this setting, because NERF usually needs like dozens of camera views of the object to fit. Here we just have a single view, right? There's actually a great paper from TPIC called Score Jacobian chaining. It's actually concurrent with Dream Fusion, which looks at how you can use diffusion models with NERF. And so you actually can take this approach and plug it into that in order to learn a NERF with 0, 1, 1, 2, 3. And this will give you a full 3D object. So this is very computationally expensive. We don't really have the GPUs to pull this off. So the resolution's too large for what the GPUs we can afford. So this is the results we were able to get when we submitted the paper. It's appearing at ICCV at this conference. We like the results. They're good. They're not like, they wouldn't think they were amazing, but we really like the results. But what's really cool is just because it was all open source, there's like been various people improving this more and more and more. And there's a really cool pull request on GitHub of just like advancing this. And so, here's improving this to actually work on improving the resolution and really making this work for 3D reconstruction of various complex objects here. And you can get normals from this and everything. So start to wrap up here is, we benchmarked this on a bunch of different data sets as well. Across different metrics, we do better at the time. There's better approaches now. Like there's papers coming out like 0, 1, 2, 3, 4, 5 has come out, and all these other variants and improving this more. I think one cool thing about this is just the scale. Like one question is like, how much data do you need? This is a plot showing how big your 3D data set is. So the 2D data set is fixed. It's always the 5 billion examples, but this is how much 3D data you have just to learn those camera controls. And so the rightmost plot is 0, 1, 2, 3 XL, and the 800K is just the regular 0, 1, 2, 3. And you can see, right, it still improves. There's no surprise. More data helps, right? But you are starting to get the returns start to diminish, right? This is an order of magnitude increase for a relatively, small gain in some ways. So I really think the future of this is going to be taking advantage of all the 2D data that we have. So with that, I'm happy to take questions. Thank you.
Thanks for the talk. I'm personally very excited about neural symbolic model. I think that what we did is quite it's very close to the exactly correct path that the community should be taking. But it's known that for it's known disadvantage of symbolic models compared to purely visual models that need a lot more manual labor. So, for example, like defining all these primitives and also collecting data. So they have two connected questions. But first, how much manual labor were involved, and what do we need to do to build this model? And the second, how much data did you have, and how do you collect it?
Yeah, that's a great question. I'll actually push back a bit on the need more labor, because I've heard that, like, I've heard in industry there's like training a large model is a lot of labor. Like you got to babysit it and make it work very well, right? But you're right. So basically there is some work in sort of building each of these tools. You got to build out enough tools, right? So that is kind of some engineering work that has to be done. But I actually think that's an advantage, because you can build this up over time, right? Like if I want to come out with a new, so let's say someone builds the next best, clip type thing. It's actually easy to swap in. I don't have to retrain the whole model. I can just, swap out the implementation of this, and it will start to use it. Or if there's a new capability that someone develops, a new vision capability, like for example, there's no tracking system in this, right? So that's easy to add. Actually, it's just you add this tool to it. So in that sense, it's modular, which is something we don't have right now, which I think in industry would be fantastic, right? Because you just don't have to train from scratch all the time. In terms of training data, there's no training in the system. This is actually all prompt. We do give, so basically the prompt's in the paper at the very end. You put the full prompt. And basically the two parts of the prompt, there's documentation as to what each tool does. So we have to write that. There's a little bit of prompt engineering that goes into that. And also a couple of in-context examples of how to use this. We were honestly surprised. You don't actually need the in-context examples. That's just in-context examples are mostly to constrain it to if the data set expects yes and you're saying true, you need in-context examples to make sure that that's aligned. But otherwise, you don't need the context example for itself.
All right. Next question.
Thanks for the talk. So this is regarding GPT. So when I look at the code examples and the images made, I wonder how low does the code generate this? For example, the example you had is that the second man to left or something. So what happens if I ask him that question? Is low the code generated there? Like if I ask for the fifth man or something like that?
Oh, yeah, very good question. I guess it will give you an exception, because the program generation is blind. So it's gonna in the current version, it would try to find it would sort and try to find the fifth man and fail at doing that, right? So this is something. This is also a failure mode that I think needs to be put in some sort of replanning. As you run the program, things might not go as you expect. You got to adjust the program as you go. So that's also a very interesting failure mode.
All right. Time for one last question. Then let's thank the speaker.
Thank you.
For that. Thank you. All right. That actually
Hi, everyone. My name is Aditi Raghunathan, and I'm a professor at Carnegie Mellon. Thanks to the organizers for inviting me to this workshop. Today, I'll be talking about rethinking fine-tuning to mitigate feature distortion. So this is the Big Models Adaptation workshop. So we're all excited about how to use large-scale pre-trained models. But just get everyone on the same page. So today, if you wanted to build a state-of-the-art machine learning model, then you'd first start with a pre-trained model. So this pre-trained model is trained on diverse, vast amounts of data. And then when we have this pre-trained model, we adapt it to our particular task of interest. So of course, there's a lot of excitement about using these large-scale pre-trained models. But what got me personally excited about these models is their potential in improving robustness to distribution shifts. So one of the core challenges in actually deploying machine learning systems reliably in the wild is that they're often not robust to distribution shifts. A canonical example is self-driving cars, which turned out to be much more challenging than expected because they often have to deal with distribution shifts, for example, where they might have been trained on typical instances where pedestrians are using a crosswalk, but when they're deployed, they have to deal with things like pedestrians jaywalking or skateboarders or animals on the road and so on. Not just self-driving cars, but really distribution shifts are everywhere. So in many applications, for example, in satellite remote sensing or wildlife conservation, we want to deploy these models in different regions or forests than what they were trained on, and this can lead to a distribution shift. And similarly, in healthcare, we want models to work with new hospitals or new demographics and new medical equipment and so on, and of course, robotics. So we want to make models that can be more robust to these distribution shifts so that we can actually reliably deploy them in the real world. And so one way to think about this challenge is the following. So we have a training distribution where we get data from, and models typically do well on new instances that are very similar to or drawn from the same distribution as the training data. But this is insufficient if we think about deploying in the real world, because we want the model to work on a wide range of distributions beyond just the training distribution. And so, said this way, it might seem inconceivable to actually get these models to work well on new things that are so different from what the model has ever seen. So maybe it's not that surprising that these models do not work really well. And so this is where pre-training is interesting, because now pre-training, we actually see a vast amount of data. So all of these new instances that we have are not really unknown to the model, and the model has a much richer understanding of the world. And so if we were to adapt these pre-trained models, there's some hope that actually we're able to better tackle these distribution shifts that might occur beyond just the narrow data that we have for our task. And this intuition does actually play out in practice as well. And there are many examples of this, but as an example here, this is from OpenAI's blog post on CLIP. So you can see we're comparing two models that obtain the same performance on ImageNet, but we can compare how they perform on distribution shifts like close to ImageNet. So they're different kinds of images, but are similar to ImageNet in terms of the final task. So CLIP is trained on much more data, and we see that it outperforms this ImageNet ResNet on all these distribution shifts with quite a noticeable gain in many cases. So this general idea that we had from the previous slide, that pre-trained models should actually help with robustness, does play out. And in general, more data does help the model have a richer understanding of the world that helps it do better than just the training distribution that you had labels on. But this is not the end of the story. So I just want to caution that, yes, the pre-trained model has seen a large amount of data, but during this adaptation process, where we help the model specialize to our task of interest, we are still doing that adaptation on a narrow distribution on limited data. So this supervision during the adaptation process is still coming from limited data, and it's not at the scale of the pre-trained model. And so we still run the risk of overfitting. So in other words, do we actually preserve the performance in terms of going beyond what was seen during the adaptation or the fine-tuning process? So in this talk, we'll focus on how do we do the fine-tuning such that we can better retain information from the pre-trained model that has been trained on much diverse data while we are fine-tuning on a much narrower data. So what goes into designing this fine-tuning process, or what choices do we make? So the choices are basically the same as we would do if we were to train a network from scratch. For example, we would think about the model family or what parameters to update, the loss function and hyperparameters, and so on. So what I'll try to show in this talk is that some of these choices, which are sort of knowledge that's been passed on from just how we train models from scratch, actually have to be rethought when we're trying to think about fine-tuning, especially with this axis of really trying to preserve maximal information from pre-training beyond just that distribution that we fine-tune on. So in this talk, I'll focus on two aspects of this. One is the model family and the loss function. And so we'll dive right into thinking about how do we choose, or how do we think about how to update the different parameters of the model during the fine-tuning process. So one way to do this is to actually examine two very commonly used methods for fine-tuning and see how they compare, and use that to build intuition about what's the right way to do this, if any. So we'll compare linear probing and full fine-tuning. So full fine-tuning is often just called fine-tuning because it's really the de facto standard when people think about how to fine-tune models. So for example, we take our pre-trained features, and then depending on the task that we want, we append a linear head. We randomly initialize a linear head, and then we use a task-dependent loss function. For example, it can be cross-entropy for classification, and then we backpropagate through the network, and we update all the parameters as we do so. So this is the usual standard, and this is what you would do if you had enough memory and compute to do so. An popular alternative is linear probing, where we take the features as fixed or frozen, and so we only update the linear head. We do not pass on the gradients to the features. We keep the features fixed. So we can try to first build our intuition about how these two methods perform. And if I were in person, this would be a quiz, but you can just think about this as we build the slides. So let's consider one example of a distribution shift. And so we don't have to go into the nitty-gritty of what the shift is, but we can think of getting the shift from ImageNet, where we have the train and test as two different subtrees of the ImageNet category. So for example, if we have certain animals, we have some breeds in the train distribution and the other breeds in the test distribution. And so we start with a pre-trained model, which has seen unlabeled ImageNet images, so has seen unlabeled data from this entire train and test distribution. But we're trying to fine-tune it only on labels from a narrower train distribution, and we want to see how it works on the test distribution. So first, let's look at the in-distribution performance. So in distribution, we see that both linear probing and fine-tuning improve overtraining from scratch, which is a sanity check that having a model that has seen richer information about the task actually does help, and it improves both. And fine-tuning actually further improves because we're able to update the features to better specialize it to our task. Now we can see what happens out of distribution, which is on unseen species, or unseen only during the fine-tuning process, but seen during the pre-training process. So the first question is, do we expect linear probing to do better than training from scratch? So if you've guessed yes, that's right, because linear probing starts from a pre-trained model that has seen more, and so it's more likely to do better out of distribution, and that is true. Now we can try to compare fine-tuning and linear probing. So we saw that fine-tuning does better in distribution because your features are able to specialize to the task. But what about out of distribution? And so maybe people are thinking, especially because we're bringing up this question in the talk, that maybe the answer is no. And turns out that this is actually the reverse trend we see here, where while fine-tuning did improve over linear probing in distribution, out of distribution, turns out that linear probing does better than fine-tuning. So conventionally, the idea was that you should just do fine-tuning if you can, and that's just strictly better. But we see that if we think about this robustness question, it's actually the opposite that's true, and linear probing, which modifies less of the model, is actually more robust. Now we can repeat this exercise with a different distribution and a train and test split. So here we're talking about the CFAR10 data set, and that's the training distribution where we do the fine-tuning, and the test distribution is a near replication of the pipeline, the CFAR10.1 data set. And we're again using a pre-trained model, which is MoCo from ImageNet Images, which has, of course, seen more data than the train distribution. And so we've removed from scratch because, clearly both linear probing and fine-tuning are better than scratch, but let's see how the two compare to each other. In distribution, we see the same trend as before, where fine-tuning was better than linear probing. And here out of distribution, we see that in the previous case, linear probing did better, But here we see that the reverse is true. So fine-tuning actually continues to do better than linear probing out of distribution as well. And so to summarize, the picture is a bit nuanced. So it's not like one method is strictly better than the other out of distribution, though in distribution, fine-tuning strictly dominates. And so we did this over 10 different data sets with different pre-trained models, including CLIP. And what we see is that in distribution, the common wisdom is true that fine-tuning works better. But out of distribution, the picture is actually more nuanced, and turns out that linear probing does better than fine-tuning out of distribution on 8 of the 10 data sets. So the data sets in which fine-tuning did better were things like CFAR 10.1, where the distribution shift was really small. And so the the models were like much closer to the in-distribution. So when the distribution shift was large, it turns out that linear probing did much better than fine-tuning. So in our ICLR paper, we have some theory about why this is the case. Like, why is it that fine-tuning can sometimes do better in distribution, but underperform linear probing out of distribution? But in this talk, I wanted to give some intuition for what might be going on here in a simple picture. So suppose this is what our pre-trained features look like. So we have 2 classes, and we have 2 different distributions in and out of distribution. And let's say our pre-training was really good, and so the representations captured some of the underlying semantics, which is why the X's are to one side, the O's are to another side. So now let's try to think about what will happen when we're trying to do full fine-tuning with these features to separate the X's and O's. So what we do is we first initialize a random linear head, and then we pass gradients through the linear head and the features. And what happens in this process is that the features will move to so that the linear head is optimal, and the linear head will move such that the features are optimal. For example, this is how they will co-evolve with each other. So both the features and the linear head will change, and because of the way this gradient descent is happening, is like each time the features will change to accommodate the linear head and vice versa. So what might end up happening is the following, where we end up in a situation where the head is fine and works well in distribution because they've both moved in sync with each other, and we end up separating the data well. But notice that when we're updating the features, we're only updating on a narrow distribution. So we're only updating on the blue points, whereas the green features might remain more or less unchanged. And as a result, the blue features have changed, but not the green. And so the head, which is fine for the new sort of distorted features, the blue features, no longer performs well on the green points. So we have this kind of feature distortion, where since we're updating the features only on one distribution, we might break the correspondence that was originally learned between the in distribution and out of distribution. And linear probing, on the other hand, doesn't have this problem because we freeze the pre-trained features. So as a result, we'll just learn this linear head, and this head performs decently on out of distribution examples as well. But we have this other trade-off that these features were not perfectly separable, and as a result, the head doesn't perform really well in distribution. And so, for example, gets a few points wrong. And this is something that we're giving up because we're not able to update the features. And so this is why in distribution, fine-tuning or full fine-tuning actually does better. But in the process of updating the features, we might have destroyed the correspondences that exist between in and out of distribution points, leading to this kind of trade-off that we see here. So one takeaway here is that this question that we had before, which is like, how do we retain this information, is actually quite, it's not obvious. Because, for example, when we do fine-tuning to like really specialize to this task and do well, we end up distorting the features, we end up changing the parameters, and as a result, we are doing we are kind of forgetting some information or doing poorly out of distribution, where there are other methods that would have done better out of distribution and better preserve the pre-trained information. But in some sense, we should be able to get the best of both worlds, because there is a method that can actually retain this information. So how do we kind of bridge this gap and like really specialize in distribution to the task, but also do well out of distribution? So let's try to build intuition for this by answering the question. So why does full fine-tuning do better in distribution? So it's trying to get at the fact that the features might not be perfect, and we do need to update the features at some point. But then it did worse out of distribution because we changed the features too much. And so a natural question is, can we change the features to make them better suited to the task? Can we refine the features, but do that in a way that's as less as possible, and so we don't distort them too much? So can we make sure we only update the features as much as necessary in order to get fine-tuning to do well in distribution? And so the idea here is that one of the reasons the features were changing a lot in full fine-tuning is because we started with a random linear head. So when you have a random linear head, then the features will also change a lot to make that linear head optimal, which is starting from a random direction. And so that actually means the features will end up moving a lot. So we can avoid this. We don't need the features to work well on a random linear head. Instead, we can try to find the best possible linear head that is possible with the current features, and then try to refine the features. So this will make sure that our features change as less as possible, and it changes to accommodate the best possible linear head. So that leads to this two-step process of LPFT, where we first do linear probing and then do fine-tuning. And we can prove in the theory settings in our paper that actually LPFT dominates both linear probing and fine-tuning, both in distribution and out of distribution for some simple settings. And so really the intuition here is that this method tries to capture what we want from both. So it does allow us to refine the features, but only refine the features in a constrained manner so that we're not trying to fit a random linear head, but really the optimal. So we've done the best that we can with the linear head, and then we refine the features. And so we can see this, tested on all the data sets. So this is like a very simple modification to the method because we just do linear probing and then fine-tuning. And we see that on all the data sets, we do improve both in distribution and out of distribution over the best of linear probing and fine-tuning. Right, so this simple tweak to how we do the adaptation really helps us achieve the best of both worlds. And so this is something that actually only comes up for fine-tuning or using pre-trained models, where things like the initialization of the head can make such a difference in performance. And so this is one example of how we really want to be careful about which parameters and how we change them so that we can maximally retain information from the pre-training process and not end up overfitting while we're doing fine-tuning. Okay, so that was about the first part on like how we have to be careful about what parameters to update. And through similar lens, we'll also examine what about the loss function that we use during fine-tuning. And to go into this part in particular, we look at using clip pre-trained model. You have these zero-shot models or like image language models. So as a quick recap, of course, everyone here is probably familiar with how clip model is trained, but we have an image encoder and a text encoder. And during the pre-training process, we have embeddings of the images and text, and we try to maximize the scores such that the image and the text embedding have the highest dot product or score with each other. So this is a way of aligning the image embeddings with the text embeddings, and that's how we get that's how clip is trained. So what we normally do for fine-tuning is the following, right? So we take the image representation as it is, and then we train a linear head, or we could do full fine-tuning where we update the features as well with some cross-entropy loss. And if we remember from the previous slide, this feature distortion is actually an important problem. And so we can now question, is there a way to actually use these image embed? Is there a way to actually do the fine-tuning process so that we're changing things as less as possible? So one thing that we notice here is that the fine-tuning process, or this fine-tuning loss, and just the fact that we're using only the image embeddings is quite different from the pre-training process. And so one thing that we were curious and ended up trying in this ICCV'23 paper is the following. So let's try to make the fine-tuning process mimic the pre-training process with the intuition that this should kind of change features a little less because the loss function or the loss landscape is not that different from what the model was pre-trained on. So in particular, the way we do this fine-tuning is similar to how people use clip for zero-shot classification. So you take your labels and you generate text embeddings from all of them. And then when we're doing the downstream or this fine-tuning, we do something similar to what the clip loss does, which is to try to maximize the similarity between the images and their corresponding correct text labels. right? So in principle, it gives the same information as supervised training, where you're telling which each image what's the corresponding label, but we're doing this in a way that's very similar to how the model was pre-trained. So this is what we call the fine-tune like you pre-train or the flip loss. And we find interesting performance gains from this simple change to just the loss function. So in this plot, what we're showing here is kind of the entire trade-off curve between in and out of distribution on ImageNet. So the way we get these curves is by ensembling with the zero-shot model. So if you can see, the zero-shot model is this diamond on the bottom left here. So if you follow the full fine-tuning curve here, we see that the in-distribution accuracy can typically improve, but then the out-of-distribution, we actually don't see gains, and zero-shot is the best model to do out-of-distribution. And now we can compare different ways of doing fine-tuning and see the curves that they traced. So when we do full fine-tuning compared to LPFT, if we just look at the endpoints, we see that LPFT does show what we saw before, which is that the out-of-distribution is higher than out-of-distribution, or the robustness performance is higher than if we just did full fine-tuning. And there's another baseline which tries to prevent distortion, like L2SP, which is trying to regularize your weights in like the L2 loss between your fine-tuned and pre-trained weights to be small. Now, by just changing the loss function, we see that we get this like orange curve here, the flip curve, which has like a strictly better trade-off. And so this is really interesting because even the endpoint has better in-distribution and out-of-distribution performance without doing any LPFT or any fancy parameter updates or anything. So we just do the same normal fine-tuning where all features are updated, but we just change the loss function. And we get much better than all the other baselines when we look at the effective robustness that we can get. So we get the highest robustness by simply changing your loss function to look like the pre-training loss, though we have not given any extra information in the fine-tuning process. And so what we discovered is that the same pre-training loss can actually help to reduce distortion, and we can measure this in terms of how much the parameters have changed and subsequently improve robustness. And we also try to change the flip loss in some sort of clever ways. For example, one problem that we have with this contrastive loss is that in the same batch, you might end up with many images of the same class. And so the contrastive loss function will also tell you to like take the same image, but like move it far away from the representations of other images, but still with the correct class. So we can have this sort of contradicting or like conflicting information. And when we try to be smart and remove these conflicts from the batch, we actually saw that the performance did worse, like the models did worse. This was really interesting and sort of suggested that there's some interesting regularization process going on by just the fact that you're using the same fine-tuning loss. And we also see gains in a few-shot learning setting. So here's the table with 2 data sets, and this is 4-shot setting. We have like more numbers in our CBPR paper. And of course, I feel like the boundary between few-shot learning and robustness is kind of blurry. So even here, we are like shown very limited supervision. So there's a higher chance of sort of overfitting. And so we want to be careful. And again, things like the fine-tune like you pre-train, which sort of minimizes this feature distortion, seems to improve performance in just this few-shot setting as well. So this is another example of how we have to be careful about the loss function that we use when fine-tuning. And again, it's a very different paradigm than training from scratch when we were to think about like how do we make these choices. And it seems to be something about using the same loss as the pre-training that really drives these performance gains and keeps the parameter distortion less, and as a result, improves robustness. So to summarize, pre-trained models, especially when they're pre-trained on vast amounts of data, and we're only seeing models getting better and better. And this is really exciting because they give huge improvements in accuracy and, of course, huge improvements in robustness to distribution shift. But then how we fine-tune them can actually also play a big role in terms of what gains we actually ultimately get from these models. And a general principle to try to keep in mind is that we want to minimize distortion, because remember that when we're doing fine-tuning, we're still fine-tuning on a much smaller limited data compared to pre-training. So we want to ensure we don't overfit and we keep as much of the gains as possible. So we want to minimize distortion. And in this talk, I talked about 2 simple ways to do that. One is this LPFT method, where we first do linear probing and then do fine-tuning, with the idea that we only want to change the features once the head is totally or like optimally trained. And the other idea was changing the loss function and kind of forgetting that we're not just simply doing classification during adaptation, and there's really this pre-trained model that was giving us this, that's the starting point. And so, for example, if we just change the fine-tuning loss to look like the pre-training loss, we see a lot of gains in using zero-shot models like CLIP. With that, I want to thank you for your attention, and also thank my wonderful collaborators, and also Apple, Google, Schmidt, and OpenPhil for funding this work. Thank you, everyone.